The system is coming up. Has already. Yeah, Sir has already given the idea of the today's class. Uh, the first thing I will do is set the stage. I'll say what is the problem that I'm working in within my group at UNT, and then tell us what kind of strategies and how to understand the context, how to understand the problem. So to begin with, for any research problem, it is very important to spend some time and say, okay, what problem are we trying to solve? You have to define that crystal clear, very clearly. Otherwise, it will be like hazy and confusing. So to begin with, you need to think about very clearly what is the problem and what is the context and what are the, for example, what are the parameters that you are trying to what you call modify or change, and then what are the performance metrics. Just what is the input and what is the output. Okay, so let's see whether you can understand whatever the problem definition and some examples of the context and what exactly we're trying to solve, and then what is the solution. And another important thing is I'm going to highlight a few papers that I really enjoyed reading and also currently using those ideas in my research. For example, as SARS told, interference is not a new problem. We know that we see interference or something like a crosstalk in communications. So a lot of work has been done, and then some people have the knack of presenting these ideas very well in the literature. So I'm going to refer to a couple of papers and going to show these papers, how they actually present a problem and how they make it very interesting for other people to read and understand. And then they go into something deep. The research goes into deep mathematics, but still you will be able to understand if it is presented properly. So I want you to really, especially the researchers and graduate researchers, to see how to understand a problem and how to present a problem for other people. So you may have a great problem and a solution, but if you're not able to present it properly, it's not going to. Other people won't be able to appreciate. Especially when you write a paper, the reviewers look for what is new in that paper. Have you addressed or have you read all the literature related literature, and then see have you presented the problem, have you explained it properly. So they look for that kind of innovation and good presentation, and did you connect your hypothesis to your results? If you say something in the top and then if you say something at the end, your results are not connected, it won't make sense. So another important thing is, especially when you're writing a paper, it should be like a story. You're telling something, like introducing the characters in the beginning, and then show what is the storyline. Presenting the context or the scenarios. Show the villages, show how people are living, and then at some point you slowly take it to the climax and say, oh, something important, something significant happens, and how that is presented, and then finally you come up with the ending. So, for example, I see some students writing. Let's assume X is something in the first line, and then after 10 lines again they say, oh, let X equal to something. So I ask them, do you introduce a hero every 10 minutes in the movie? No, hero introduced in the beginning. The characters are introduced in the beginning. You don't repeat them and say repeatedly introduce the same variable or same things again and again. Okay? Anyway, the essence here is I wanted to capture today's class, particularly based on everything that we learned so far. I wanted to see how other people do research, how they present the problem, how they solve the problem. Okay, so with that background, let's begin. So to begin with, I'll show you what is the research I am doing. This is we spent a few years on this. We haven't published yet. So this is a diagram that I asked my students to illustrate. So the scenario is that drones are flying from one location to another location. And imagine that in future, for example, there may be an air corridor like this from Warangal to Hyderabad. Okay. Obviously, if you are even on the road when you are driving, you don't go randomly, right? So you have a route. Of course, you have options to change the route, but still you go on the roads. You go on the highways, for example. So air corridor is like a highway. So let's assume that just like the way you have subways and for trains and also in the bus stations, let's assume that you have several vehicles going one after the other in the corridor. So we are looking at a futuristic, like maybe 2030 or maybe 2035 or 40. You may see a nice air corridor. Then there are certain locations. We call these takeoff and landing locations as vertiports. So it's like an airport. So, but here it's a miniature airport, or if we call that as a vertiport. All right. So the question here is: suppose this length of this corridor is about 30 miles or 40 miles. The question that we are addressing is how many base stations you need on the ground. So keep in mind, as of now, there are cell towers everywhere, but you need something like a cell tower, or we call it as a base station along the route rather. So which means that if this is the air corridor, then on the way along the corridor, you need to have base stations. This is again one solution. The other option is we could use the existing cell towers to provide support for drone communications by having some antennas facing up. Some antennas are facing down to provide support for our phones, terrestrial users, and some antennas could be faced up. That's also possible. So both solutions are there, but in this scenario, we are assuming that you are placing these very specialized base stations along this corridor. So the question we are trying to address is how many base stations you need to provide a continuous support. Okay. So the problem is called, actually, the problem can be addressed or in the context of what you call link budget analysis. So given this scenario, now you can see where the interference plays an important role, meaning that if you are trying to provide communication support for all these drones, then there should be air to ground communication and ground to air. So that means drones should be able to connect to the base station and base station should be able to connect with the drone all the time. This has to be almost like continuous. Now, why do you need that? Let's take two examples. What kind of data you need to pass for air to ground? For ground to air, the cell tower is like a ground control station, or you're using the cell tower. Set up a ground control station somewhere nearby, and then you are sending commands to the drone saying maybe you are providing flight plan, or you're providing no-fly zones. Any information. Those are called command and control. There's one term is command and control. The other term is non-payload information, non-payload data, NPLD. Payload data and non-payload data. Payload data means you have a camera or something and you're trying to share information about sharing sensory data, sensor information. That's called payload. Payload is something that you're carrying in the aircraft. Non-payload means command and control. Command and control are very critical, very time sensitive. So you need to provide that kind of communication. Second is the drone also up in the air has to tell its location, its heading, status, all that information back to the ground. So that's called telemetry. We call that telemetry information. So you need to talk back and forth. And this information is not really too much. So you don't really need to worry about gigabytes of data transfer. You're only sending maybe in a few kilobytes per second. Okay, maybe 2K or maybe 10K per second we're talking about. So the bits per second or data rate is not really too much. So we don't have to worry about data rate, but reliability is key thing. It has to be in time. It has to reach quickly, and we cannot afford to fail. If you miss the data, then you don't know where the drone is. Okay? So you need to have high reliability. So we talked about that, and then let's say one drone is communicating with the base station, then obviously other drones are also going to communicate. So which means that that you need to think about, you need to consider the interference coming from the other drones. So one option is you can come up with some sort of a scheduling scheme. You can say TDMA or FDMA. We can come up with those scheduling schemes. But given that this network is not really a stable network, right? It's not like you pre-planned the network. So it's more like an ad hoc network. So one can come up with the scheduling schemes, but here we are assuming that you're not really scheduling any such things, which means that that you need, when one drone is trying to send a telemetry message or maybe a ground control station somewhere here using the cell tower to communicate like command and control information, you are not preventing other talk. So that's the reason you have interference. So this is the context. I'm just going to show you some idea, some things that we are trying to do. So you need to figure out how antennas could be facing up. So this is an example of base station antenna structure. We came up with some sort of a hexagonal pattern where you have 6 antennas on top of the base station facing up, providing communication. Okay. I'm just giving the highlights. Okay, I'm not going to discuss this paper, but I want to set the context. And then the things that you need to think about before you present the problem is, what's the transmit power you are giving, and what is the base station height, and antenna properties or characteristics, what carrier frequency you are using, and those kind of things. And then primarily it's almost done, where the problem is almost finished, but we are making sure everything is coherent. Again, the story is coming across well and all that. So the problem that we are trying to do is something called link budget analysis. So once we start with what you call the path loss model, and this will give you only some part of the signal degradation. Path loss is one component, but that's not enough, right? In terms of characterizing the received power, you received power something, it will be something like this. For example, you are adding some other terms here, where this e power minus alpha d, in addition to this path loss, you are also multiplying with some other component, and that to do with the losses in they are to do with the losses in the atmosphere. Let me show you for completion what that. See, attenuation due to atmosphere or losses. Basically, you are adding a term to include the attenuation, and then you don't have to do everything from scratch. I was mentioning before that there are ITU standards. Now, how do you take into account the loss due to like fog, or loss due to some atmospheric all these conditions, atmospheric conditions. So those you can simply use so go to the literature and get the data. The other things that you can also think about rain, attenuation due to rain. So instead of going into fine details, you abstract the loss and come up with an empirical result, empirical formulation, and that you can include in the model like this. You're saying the last term is to include this particularly is towards for the losses, additional losses. Okay, and then finally, I'm bringing some couple of important things. Normally, as Professor Sai Prakash mentioned, this is the formula we use. But the correct term is, in addition to noise, you also include SINR, include the interference. So, but to begin with, for undergrad classes and understanding what kind of data rates you can get, we use this formula, Shannon's formula. But practically, we also have to take care of the interference. Another interesting thing, some of my colleagues are working on frequency reuse. So one beautiful result that came out from the literature is, on the ground, you partition the coverage area using hexagon as a base structure. But in the 3D space, researchers found, a couple of researchers, and one of them is my colleague that I was working on, they came up with the basic cell in the 3D space is octahedron. More specifically, it's called truncated octahedron. So if you read in the literature, fundamental cell, or you can call air cell, for example. So fundamental cell structure in 3D space seems to be the octahedron. On the ground, whenever you look at cellular coverage, typically we use a hexagon as a base model. So that is some interesting thing that came over about 3-4 years ago. So what is the idea? So for example, if one base station is covering this volume, another base station is covering this volume, then you divide this into these cells, and whatever frequencies you are using, whatever channels you allocate in one small cell cannot be reused in the adjacent cell, but you could use in the other cell. So the idea of why are we coming up with this cell structure? To enable frequency reuse. So what do you mean by frequency reuse? That if you are allocating set channels in one cell, it's possible that you may get interference from the next cell. So here you cannot use the same frequencies, but the third non-adjacent cell, you could use the same frequencies or same channel that you are allocating in the third cell. So that is the idea that being explored here. But in the original problem that I am discussing, we are not thinking of frequency reuse. It's more fundamental, more basic, in the sense every drone is talking, and then every other drone is causing interference. So there is only one signal that is of interest to us. All other signals are interference. For example, just to give a realistic example, let's say Professor Sai Prakash is talking to me, and at the same time all are talking. Then so all other talks will be interference. Or I'm addressing Sumit, right? If I'm talking to Sumit, every other talk, even though they are important, it is every talk is important, or every conversation is important. But at a given time, if Sumit is trying to convey a message to me, or I'm talking to Sumit, just like the way a drone is trying to talk to the ground control station for some critical data, then even though all talks are important, but in that time, all other talks are going to be crosstalk. That's interference. So that's what we are modeling. We are not considering frequency reuse and all that in the fundamental problem. But later, if you come up with the frequency, what you call multiple access technique, you can build on it. And now, can you recognize this term? This is the signal to interference ratio. This term, in fact, typically this is what we use. This is the same variable, same symbol we use for interference, signal to interference ratio. So this comes from this. It's a textbook thing. It's nothing new here, but we are only applying. We are only using this formula to estimate the interference in the given context. So the problem is different because we are looking at air to ground or ground to air communication. So the challenge is that, so given this equation, this is the noise, and this is the interference term, and this is the power. This is the signal power, and this is the noise plus interference. So when you say SINR, what does it mean? Signal power over interference plus noise. So that the idea is very clear. Everything else is straightforward, but the only thing that is critical is to what is the interference? How do you estimate the interference? So you need to come up with a model for estimating the interference. Okay, so that's the idea. I'm going to quit this paper, and this is to tell you, to give an idea about what kind of problem we are solving. And again, the context is how do you provide communication support for drones flying in the air in an air corridor, to be specific. And that will tell us, once you have this kind of the channel model, path loss model, interference and all that, you can come up with, you can answer this question. If you have a 30-mile stretch air corridor, how many base stations do you need? For example, more specifically, from Warangal to Hyderabad, it's about, I believe, 120 kilometers or so. So given that distance, how many base stations are dedicated base stations? We are only looking at dedicated base stations. And this is not a hypothetical. In real world, in the place in the US, there is a company called Aura Networks, AURA. You can take a look on the internet and see they have license to provide this kind of base stations dedicated for drone support. And they are using 433 megahertz. So they got a what you call license for the whole country to use 433 megahertz. Yeah, that's the part. If you have a lower frequency, when you say 433 megahertz, less compared to 2.4 or 5, right? So if you use lower frequency, you can go for longer distances. In fact, I think LoRa is an example. If you I think the frequency is probably how much? 470. Yeah. So that's the advantage of using lower frequencies. The other thing is here when you use LoRa or even 433 megahertz, the key thing is you want to send command and control. See, you're using that link specifically for command and control. So which means that packets are small. You're not really worried about a lot of data. But what is important, what is more critical is, are we able to establish a reliable communication? Because command and control is very critically important. So they're not talking about large data sets. You're not sending video data and all that. They don't. So another critical example, another use of this command and control link is to alter the route. Suppose you are in the middle of the air, something happens somewhere, and you need to change the route. So what do you need to do? You have to send that command, the new route, so that the autopilot in the drone can change the plan in the middle of the flight, which is critical, right? This is a critical information. Just like the way you are sending any critical commands like move left or right, starting from simple commands like that, you can upload the entire route from point A to point B, in the beginning, but then in the middle of the flight, something happens, you want to send those commands. Same way, drone also wants to talk to the ground controls. Suppose there is something happened, maybe there is sensor failure, or maybe a propeller damaged, or some bird struck the vehicle. All that kind of information, it has to talk to the ground controls. It's like a two-way communication, right? So make sure that you see the value. But then let's get into the basics, and I just provided the context for now. What is the advantage of, what is the reason why we want to model the interference, and what is the reason a good doesn't have to be perfect, but a reasonably accurate channel model, path loss model, interference model will allow us to figure out what to expect, how far you can communicate, what's the range you want to expect, and how much area or volume a base station can cover. And then what kind of data rate you can expect. All those things can be answered based on these models. And then I'll give you now the background in the sense of, I have a small presentation. You all have that with you. I will go over those few slides to explain how others have presented. What's the literature? Basically, it's like a literature study. So my PhD student, Atif Iqbal, he prepared this for me referring to few articles that are few relevant articles. Yeah, depending, the applications are many. You could use, we are using unmanned aerial vehicles, and the problem is relevant. Understanding the channel, understanding what you call the channel data rates and interference. All these are relevant in the context of many applications, including IoTs, emergency applications and transportation. And our goal is to see how do you design the network, how do you design the communication system, including the base station and channel allocation, all those parameters. How do you design a system to minimize the interference? When you talk about optimization, this is one problem. Given the parameters, remaining parameters are fixed, how do you minimize the interference will be of interest. Of course, frequency reuse techniques are also will help us to minimize and to deal with the interference more effectively. Yeah. So one thing is about understanding actually the context, meaning that where are we expecting the drones to fly? I gave you two altitudes. One is, even though we are staying low altitude, but there are two levels. Very small drones for agricultural applications or surveillance, drone deliveries, all those happen at about 400 feet. Now this is, by the way, why did we choose 400 feet? This is a regulation from the aviation authorities. Small drones under 55 pounds of total weight, they are allowed to fly only at or below 400 feet. Then other level is almost 10 times higher, which is 4,000 feet. When I say 4,000, it's not set in stone, but about 4,000, 5,000, maybe 6,000. Those are the altitudes. Yeah, those are the altitudes at which large vehicles are going to fly. I'm referring to above ground. Okay, so sometimes in altitudes you're going to see two levels. You need to look at it carefully. If suppose somebody says, "Oh, the aircraft or air taxi is flying about 11,000 feet," you need to say, what are the units? Is it AGL, above ground level, or mean sea level? Okay, for example, if a city is about 4,000 feet above mean sea level, then adding to another 6,000 will only become 10,000 or 11,000. It doesn't mean that you are flying at 11,000 feet, but it's possible. And it's possible that large vehicles like helicopters or the vehicles what we refer to as electric vertical takeoff and landing, eVTOLs. Those vehicles can fly higher altitudes, but not too high. Probably anywhere between 4,000 to maybe 10,000. Okay? But the altitudes that typically I've seen vehicles flying about 4,000 feet or 5,000 feet or 6,000 feet. A quick way to convert feet into meters is just divide by 3. It's just a thumb rule, not accurate. But suppose when I say 400 feet, divide by 3 to get into meters. But generally the point is we're talking about two levels. One level is about 400 feet, the other is about 10 times. So those are the things that you have to keep in mind. And so when you are modeling, try to be realistic. Why we have to be too much into, even though it's a theoretical model, when you build a model, try to be as realistic as possible. For example, what frequencies are we going to use? Here I used 1 gigahertz or 2.4 gigahertz because we don't know what frequencies are allocated. The frequency bands allocated for drones is, it varies in different countries. For example, very recently in the US, they allocated 5 gigahertz band. A small band within about 5 gigahertz has been used. So get familiar with those if you are interested in working in this area. You need to be familiar with what frequency bands are used, and not only for drones, you can think about non-terrestrial networks. What kind of bands satellites are going to use? It's good to know. Otherwise, you will be very far away as such, academics are far away from the industry. So, you don't want to think everything only in the lab. You want to connect with the reality. But in that context, I believe next few days there are some academic research, academic and industry collaboration. Some shows and exhibitions are there, I believe, on the campus. Okay, now, so look at when we immediately after talking about interference, the next bullet says stochastic geometry used in the model to interference. So there are two things. One is stochastic geometry, the one term, and the second thing is in the talk that you heard on Saturday, Professor Venka from IIT Hyderabad, he talked about Poisson point process. So I saw not only that I'm using this in my research, but I also want to show you a couple of papers that give you the background, not only about the mathematics, but how those Poisson point processes and stochastic geometry are used in understanding or estimating the interference in cellular networks. And the other thing is the papers that I'm referring also, they're beautifully written. That means we are going to go through first few sections to show. I'll walk through that those two sections to give you an idea about why the papers are well written, why the papers are so good, and what is the consequence. If you write a good paper, people will read. If you don't write, nobody cares. It will be somewhere lying in some shelf. So how do you measure that performance of the effect? The impact of good research is felt through number of citations. So for example, the paper written by, his name is Muhammad Aluni, very well-known professor, contributed significantly to the world of communications, and that paper has about hundreds of citations in few years. Okay, so now we are connecting to the mathematics. Okay, so we understand what do you mean by stochastic geometry, and my goal is not to explain the mathematics, but how we are using them, how we are using Poisson point process and 5G, or sorry, stochastic geometry. It looks like 5G, but actually it's SG. For especially understanding the interference, because if you don't understand if you don't model accurately, then your channel model will be imperfect, and your path loss model or your signal to interface ratio, all those will be incorrect, and then your estimations of data rate will be incorrect. So that's the reason the focus is on interference today. Today's class is about interference. And then what do we do with this? There are many things. In fact, I'm going to show more, but the performance indicators are typically measured in two: probability of receiving a signal, which means that whether if the drone is sending a telemetry information, is the ground station getting it or not? What is the probability? You wanted to keep it high, like 99% of probability. So you can estimate this using the theoretical modeling. You can estimate what will be the probability of receiving signal that you can expect. Of course, bit error rate and all those things too. Bit error rate is common, but not only that. But not only bit error rate, you need to think about probability of receiving a signal. That is outage probability. It's very common. Outage probability means the link is gone. So what's the probability of link gone? And then obviously you want to keep it minimal. So what do we know? We know so far the significance of the stochastic geometry, the significance of modeling the interference, and then what are the outcomes we are expecting from this. So I hope you see that. I set the context in terms of set the stage for us to get into the details. And every slide has a reference. And this is one of my friends. I closely work with him, Professor Metalak from University of South Carolina. So he has contributed significantly to this topic, air-to-ground propagation channel modeling. Whatever we talked about in the previous, especially yesterday, we talked about generally channel modeling, right? We talked about parameters like path loss, fading, small fading, and small scale and large scale fading. All those are textbook things, but he actually applied them to do some pioneering work in the context of air-to-ground. So this paper is, you can search for it, and in the references you see the reference, and it was done 2019. And let's take a look at other things. As I mentioned, we need to be realistic in the sense whenever you are modeling, whenever you are doing research, make sure that you are choosing the parameters properly. So here we are referring to like for UAV communications, normally L band and C band are used, and those are 2.4 gigahertz and 5.8 gigahertz. The reason, can you think about why we are saying take this bullet and try to interpret why 5.8 gigahertz has less interference compared to 2.4? That is one reason, yeah. But more importantly, this high frequency, right? High frequencies have less coverage, so lesser volume will have less interference. So, for example, in the project that I am working on, drone to drone communications, one of the program managers who actually funded this project from NASA I asked him actually, what should be the range? He said, Kamesh, don't fix the range. Give me a tunable model. I mentioned this before, I'm repeating it because it's the context. Suppose I want the range to be 2 kilometers. So how do I adjust my parameters? And then what if I want to change from 2 to 5 or 5 to 10 or 10 to 20? But in all these scenarios, the most important thing is, generally if you look at, if the range is 2 kilometers, you expect few drones to be within the 2 kilometers, right? So interference will be limited. See the connection, your signal is not going beyond 2 kilometers, but that's the meaning of range. So if you design a system to communicate to drones or vehicles or phones within 2 kilometers, that means you're expecting, you're saying that after 2 kilometers you won't get my signal. So which means that you have to worry about the nodes which are causing interference within the range, within the 2 kilometer radius. Suppose you change to 5 kilometers, then you are increasing the range. It's good, saying that my signal can go up to 5 kilometers, but not beyond. So which means that number of users in that 5 kilometer range or radius will be more. Same thing with 10. So on one hand, it's good to increase the range, but also you have to worry about more users, more interference and all that. So, okay. So some of the other related things that you need to know. For aeronautical communications, obviously, not only drones, we also have to deal with, even what you call commercial aircraft also require proper communication support, right? So LDAX is a technique, LDAX, L-band digital aeronautical communication system was studied or developed for aeronautical communication for commercial aircraft. Of course, we could use the same thing if it is approved. We could use the same thing for commercial drones also, but drones have different requirements. Drones are small and they fly at different altitudes, and you don't want to interfere with the commercial aircraft systems. So drones are using different bands, and then you cannot really put large systems. Your payload has to be limited. So for example, some of you may remember ADS-B is used as a transponder for communicating to commercial aircraft and also from commercial aircraft to the ground control station, and that was called ADS-B. But ADS-B as it is is not recommended to be put on the drones. Instead, we are using something called remote ID. So you cannot just port things that you are using for commercial aircraft to smaller aircraft. Yeah, and then there are also a few other things that we need to know. Aircrafts obviously are in 3D, so 2D model that we develop for the ground will not be sufficient. So you need to develop different 3-dimensional models. And then one more important thing is, look at the bullet, the third bullet. It's kind of interesting. If you're only flying only one aircraft in the air, then yeah, you enjoy the strong signal because you get a line of sight, good line of sight. So point is, air to ground communication will have the ability, or it enables very strong line of sight, because you can't expect when you go out and trying to communicate with your trying to provide a communication from cell tower to the airplane. It's a clear line of sight. unless it is raining or something else. But you know, other obstacles or other communications won't interfere. But the problem is, it is good to have a good line of sight. What about interference? Now extend that one drone to multiple drones. Then every signal is going to be strong. Not only the legitimate signal or signal that you are interested in is going to be strong, all other signals are also going to be strong. That means your signal is good, interference also is strong. So interference actually is a problem in airspace. You see the point? So these things you have to keep in mind. You know, these are like check rules, you know, thumb rules. So whatever work you are doing, you have to make sure that they don't violate these basic common sense things. Okay, you cannot do research that violates the common sense. Okay. Most of the time, it's reasonable to assume free space propagation for computing received power. Of course, you need to calculate, you need to include interference as we talked about. But free spaces model is only because we are using that because we don't have more accurate models. Free space is fine because we don't know anything better. So once again, try to understand the context. From drone to drone communications, we are saying you could use free space, but if you are flying at 400 feet or even 4,000 feet, you cannot rule out reflections. Okay, so until we get good models, you're okay to use free space. But if you have a good model, it is better. In fact, that's where exactly I'm working on. My research probably will be published very soon, probably in 1 year. What I'm trying to do is, at what height, for example, you can say free space is meaningful. At what height you can say, oh, free space is not valid. You understand what do you mean by free space path loss, right? It doesn't have any other terms except that you're saying your path loss is proportional to d square. That's free space. But is that exponent is correct? Is it path loss exponent can be only 2, or it could be in a complex environment it could be more. But more importantly, what I'm modeling is what would be the non-line of sight? What are those components? And at what height you can safely claim that, okay, we can ignore the non-line of sight components. Okay, the things from now onwards, whatever I'm talking, they are more important or probably more easily understood by grad students. So I would like all the researchers to pay attention to this. At the same time, for undergrad students, just because you haven't taken advanced courses, even though I will try my best to give you the picture, but don't worry about if you have difficulty in understanding, you know. But in fact, I don't have to make any assumptions. Who knows? You may be able to follow that. Okay, but I'll do my best to give the big picture so that everybody can understand. But especially for grad students, I would like you to pay attention. So this paper is that I read, published in 2024. So this provides you a context. Now, remember I was mentioning you need to before you try to solve a problem, you need to understand very clearly what is the problem, and before that, what is the context, what is the scenario. If you understand that, then you will not only be able to solve the problem, but also present it in a very simple manner that everybody can enjoy. So a paper should be enjoyable. If you read a paper, it shouldn't be boring. It shouldn't take a lot of time. There are some papers like that, because if it's a pure mathematicians writing a paper, for us as engineers to relate to real world is challenging. So some things like real analysis, they are inherently theoretical, like complex variables. These are all not easy to follow. But at the same time, then the question comes: why are you learning this? Why are universities are teaching? The reason is they are giving you the basics and a set of fundamental concepts in all the subjects. When the time comes for you to do research, you will be able to say, oh, at that time I did that. Now you can go deeper and apply those ideas to the current research. So here is such an example. So this says, this is the volume, like almost like a hemisphere. It's half sphere, right? And then what are the things that you are expecting here? There are fixed wing aircraft. So look at this icon, and here is an example. Fixed wing unmanned aerial vehicles. These are ground stations. An example of ground station is this. But there is only one ground station. And then rotary wing vehicles, unmanned aerial vehicles with rotary wing, like quadcopters. Then CA. CA stands for commercial aircraft. And then link for commercial aircraft. So these are the links for commercial aircraft. And then UAV link. Here is a UAV. These are large dashed lines. These are small dashed lines. So these are all links. Basically, any line is like a dashed line is a link. But all of them are communicating with the ground control station. Cell tower. Basically, you can call it like a ground station or cell tower. But typically, ground control station for aircraft is only for managing or communicating with the aircraft. You don't use cell tower directly, but you have a ground control station somewhere nearby, but the communication channel is from the cell tower. Then you have multipath effect. So multipath is, we talked about multipath before. So an example of multipath is here. If this aircraft is talking to the ground control station, there is one direct line of sight or line of sight or LOS, but there are non-line of sight. This signal is bounced by this building and coming. So this is an example of non-line of sight. Another example is this is actually going to the cloud and coming reflecting. So all this picture actually depicts the scenario beautifully, in fact. Okay. So even though you're focusing on aircraft communication, but there are all the context. This is like a typical urban context. Now this paper is about interference analysis for coexistence of unmanned aerial vehicles with civil aircraft, or you can say commercial aircraft. So it's coexistence means that how do you provide communication support when the airspace is filled with drones as well as civil aviation or commercial aircraft. So that's the problem. See, that is how the author defined the context. See, he is trying to solve a problem or trying to understand or estimate the interference in the context of, in the situation where there are different types of aircraft, including UAVs and also civil aircraft like helicopters. All of them are trying to talk to ground control station. We're going to spend more time on that paper in a minute. What I'm referring to is this paper. I'll going to show this paper and talk about a couple of sections to show you how this paper is, how the paper introduced the problem and how they started developing the mathematical model. So the reason is I want you to understand how researchers think about a problem and then how they present it. So we talked about the context so far. I'll go back to the same paper. I'll show the paper on the screen and we'll get into more details. But before that, I wanted to show you other papers. So we're nailing down to only one paper, but I wanted to show you few other papers that I studied or asked my student to look into. Then another paper is called Impact of Interfering Node on Unmanned Aircraft Communication. So once again, the context is, the problem is interference, understanding the interference, but a different problem. And everybody defines a different context, and they make certain assumptions, and then develop the model. So it is for us, whenever you begin your research, and sitting with the advisor and the professor, you come up with what is the problem that you are going to solve. You agree, you sit with the professor and come up with an idea of the problem that you are interested in solving. And then you have to do literature survey. So this is an example of very well defined or very narrowly focused literature survey We're only focusing on interference in the context of aircraft communication, or more specifically UAV communication. So this paper says, this paper is focused on understanding impact of one interfering node, if I'm correct, okay, on the in general on UAV communication, and they focused on in terms of output. So remember, I always was telling, what is your input, what is your output, or in terms of, if you say I want to study the performance or analyze the performance, you need to go to the next level and say what do you mean by performance, okay, and meaning that what are you measuring. So here the measurement is outage probability, okay, and what are you trying to optimize. So whenever again when you perform, typically you're trying to optimize something. In this case, what are we optimizing? Optimal altitude that minimizes the outage probability. So it's so well defined, one liner, very clear. So the clarity is required. After without the clarity, you cannot explain to anybody, and you don't even know what we are doing. So it is important in research to define, okay, I'm going to look at optimal altitude of the aircraft, and that will result in minimization of outage probability. Okay, we already talked about what is outage probability. So you need to know, you need to see why this is important. And finally, it says with increasing altitude, probability of line of sight increases, which is true, as we talked about. If you increase the altitude, you have a better line of sight. For example, let's say if you're even for cell tower, right now existing cell towers which are static, the typical altitude is about 100 feet or maybe 120 feet. But then there may be buildings which are taller than 100 feet, right? So you won't get a good line of sight. But let's say you take it further, go above all the buildings. But you don't have to go too far. But if you go too far, then what happens? Then distance from the receiver will also increase. From the ground, altitude increases, fine, you're getting a good line of sight. So one part is positive. The other part is you're increasing the distance. That means your round trip time will be, of course, it's very small, millisecond, but still it counts. Okay. So you see that. So can you see the value meaning of optimal altitude? So one hand you're getting good line of sight, good quality signal. On the other hand, you're increasing the distance, so your round trip time or latency will increase. So there is a need for optimal altitude. Okay. So this is only about probably one drone, but if you extend it to multiple drones, the question of how do you place the drones in different locations, and then figure out what is the optimal altitude for each of the drones, and also the horizontal distance, how much separation is required to be able to minimizing node. What is the optimal altitude for the drone that minimizes the outage probability is also another scenario, another context, and that is from this paper. So these papers are available, publicly available. In fact, from the guest house, when I was downloading, once I log into your network, these are all free. And yeah, so you have everything, literally information in your fingertips. Those are the days we had to, whenever we find a nice paper, we have to ask the librarian to get interloan library, and it comes after 3 days. Those days are gone. So you have everything. So you should make use of that. Yeah. Yeah. Right. Yeah. So. Right. Yeah. Out of coverage. You want to minimize or make it zero. Actually, correct. That's correct. That's the main parameter. You're absolutely right. Yeah. So we can take a break. But basically, I set the stage. Set the stage, and we know now why the problem of estimating the interference or comparing the interference is important, and we'll get into more. So we are in the process of reviewing some of the existing literature with the objective of understanding how they define the problem, how they define the problem actually, and how they set the context. And these are example papers, very well written, and I'm going to walk through at least one of them and go into some finer details. Okay. Yeah, this is a good example where same cell tower is used for ground communications as well as the aerial communications. So how can that happen? You can imagine that you set some antennas facing up in the airspace, and the other antennas facing down to support the phones or terrestrial users. So this for non-terrestrial, this for terrestrial. By the way, 3GPP, starting from release 17 onwards, I believe, 17, 17, 18, 19, 20, these are all geared towards supporting NTN. So we have to start following this. If you're not familiar with the 3GPP, I suggest that you start looking into the new releases, and 3GPP stands for third generation partnership project. But even though you see third generation, they are also responsible for 4G, 5G, 6G. So at some point, next release, one of the new releases will be focusing on 6G. So a lot of researchers are working across the world in academic institutions on 6G. 6G is primarily for machine learning and AI supported communications. How data-driven techniques can be applied or machine learning techniques could be used for communications. So typically you can say the significant feature of 6G is artificial intelligence. Okay, in general. So we need to start reading those. If you want to know what is happening in the industry, you need to figure out, especially non-terrestrial networking. I suggest that you start looking into those new releases. Pick one, like 17 or something, and start understanding. So this is a scenario where where the cell tower or base station is trying to support both ground users as well as non-terrestrial platforms like drones. So this paper is from, I think in the references you will see the publication here. It's about interference mitigation measures for unmanned aerial vehicles served by cellular networks. So in fact, most of the papers we are dealing with all about cellular service. And then this paper also is focused on interference. The key ideas are they studied the interference modeling and mitigation, then uplink and downlink. In the uplink, interference occurs because UAV is communicating to many base stations. So for example, so you are talking about one base station here, one aircraft, but there are multiple aircraft. There will be multiple aircraft, and all of them are trying to reach out to the cell tower. So remember that the cell towers are designed to support ground users primarily. So that means the placement of these cell towers, distance between them, all those are geared towards primarily for ground users. But since we want to reuse or use them for multi-purposes, it will have a different kind of, the interference will be complicated or more, because these are placed in such a way that you want to mitigate the interference for ground users. Since you are directly using them for airspace, the interference will be different. They are not optimized for, basically they are not optimized for mitigating the interference for air vehicles. They are designed to mitigate interference for ground users. So that's a challenge. Okay. Hmm. Fading will be there. Yeah, fading will be there, but yeah, that's a question actually. At certain heights, if you it's very high altitude, typically people assume it's free space class. So you don't have what you call yeah, multipath propagation is not there, but you cannot rule out. My point is like it's possible that yeah, there's supposed to be maybe the other planes, especially when there are more vehicles flying, then you may encounter the reflections or obstructions too. That's exactly what we are currently looking at. So to be more specific, I asked my student to start with an assumption that there are no vehicles in the airspace, only only your vehicle to start, or maybe only two vehicles, like two vehicles are there and nothing else, no obstructions. And since I'm focusing on the air-to-air channel model, so when two drones are talking, there are no interference. So that's how we start. We're starting in the simulation, but then we wanted to put some other vehicle in between, and we are not even looking in terms of interference. That's also important. But in that specific example, we are focused on developing a channel model or air-to-air channel model. So what we are saying is, suppose you have another aircraft, then you're going to see reflections. And then my collaborator, Professor Metalek, suggested that not only the reflections, more importantly, your signal may be obstructed. So that those things are possible. And then now think about like Poisson point process, where you're assuming high density or more number of vehicles in the airspace. Then it is clearly you're going to see multipath propagation and all that. Not from the ground, probably if you are flying at 4,000 feet, or maybe between 1 to 2 kilometers altitude, the reflections may not be so strong. So reflections are not really an issue. Or multipath propagation coming from the ground is not an issue. But what about within the airspace? And we want to see. We don't know how big or how influencing they are, but we want to study that. Right. That's also, in fact, Professor Sai Prakash and I were talking about handoff for drones, also important. Now in the example, in the previous example, when I showed you 3 base stations on the ground, yeah, which base station is going to cover, that also is applicable. That problem also is there. The nice thing is that we don't have to predict. We know which one will be next, because with a fixed route, base stations are fixed. Whereas if you are driving, like we don't know where you are going, right? Every day, you can make some assumptions like you are going to office every day, but typically, once you sit in the car, you can go anywhere, right? So where you are going to go cannot be predicted. But in the case of fixed routes, like these corridors, your location can be predicted easily. So that means yeah, that's also there. In fact, in this example, we were looking at this, right? So this person actually says, so this reflection with the clouds. Yeah. But this altitude is, again, probably we are referring to 1 to 2 kilometers altitude, or 4,000 feet to 5,000 feet. So that has to be considered. If we want to be more accurate, I think we have to study what happens at those heights. So that's the point. That's the reason I'm suggesting. When you define the context, you have to really dive deep. Both in terms of the model and also the environment. I think the more you understand, the better model you can build, and your predictions will be more accurate. At the same time, because you put a lot of work and you also take time to present this in a very elegant way, very nicely, people will appreciate your work. In fact, that's exactly the segue. Now we'll go into one paper and see how nicely they have presented this work. So before there are two papers I'm going to refer. Okay, the idea is to show you how to write a good paper. Okay, and then so first one is, I will focus more on the second paper, but before we go to second paper, let's focus on first paper on, spend some time on. So Professor Sai Prakash, this is the paper, this is one of the papers I sent you today, and this is by from Muhammad Aloni. So, and beautiful paper on modeling and analysis of cellular networks using stochastic geometry. It's more like a tutorial. So this, so that take few minutes to see. See, first of all, I'll highlight some of the statements. Despite the existence of large number of interfering sources, so point is, there are a lot of interference sources, especially on the ground. By this paper is about cellular networks on the ground. So the nice thing is, if you read this paper and understand the concepts, then we could apply them to drone communications. So that's one reason. He's saying that central limit theorem doesn't apply. Because normally you can also assume when you say central limit theorem, what does it mean? You can model things using a Gaussian distribution, but that's not the case. And then what are the influence of these obstacles? The effects are path loss. Yeah, let's take a focus on this. It's on saying that path loss and interference. So those are the major impediments, and naturally we need to look into that. And then the importance of this stochastic geometry analysis is that it will lead to this important outcome, aggregate interference. We're trying to understand, so stochastic geometry is telling us, or even let's focus on this. It's giving us aggregate outcome. So you cannot really individually do things, but stochastic analysis will provide you a way to address the effect of all these interference in single form, or a formula, for example. Okay. So I think at this point mostly grads are there and few undergrads, but I think you should be able to follow the direction. Okay. Then also want to show you something very nice formulation. This paper actually, you can read it. I sent it to Professor Prakash, and he will going to share. One more interesting thing here is, whenever you write a paper, you see how many references. You need to do a good job in terms of literature study. So one is, you will be reading, suppose you read about 100 papers. Read means you are only reading abstract, and 100 is not a large number. Okay, when in a PhD, when you look at these references, it will be hundreds of references. But what I'm saying is, once you read them, look at how they are able to categorize. So this is, what is the system that they are studying in these papers? Is downlink is studied. Here it is uplink. Here is a full duplex. Here is device to device. So they categorize these communication systems that were studied in each of this paper very, very elegantly. Okay, now coming to the main point. What is our goal? Develop a model for aggregate interference characterization using stochastic geometry. Okay, and by the way, don't be intimidated about the mathematics. We are, it's like once you get into that, you spend some time, it will be not really that difficult. If you look at on top, it's complicated. And then look at the outcomes. See, especially many of our students are. When I had discussions, I was asking you, what is the problem definition, right? And then what are your metrics? So here, look at the metrics. What are you going? What can you answer? We talked about outage probability before, and then we also talked about bit error rate or symbol error probability, bit error probability. These are things are known. Handover rate in sometimes. These are all the metrics that you can study. So what are the, when you say, oh, I'm studying performance, I'm doing performance analysis. I was very specifically, I was asking what is the performance metric? If you don't know the performance metric, then that means you haven't gone to the detail. So you have to spend time say, what is my input, or what are the variables I can play with? It's more like when you say, I'm optimizing something. What are you optimizing? Okay, when you say I'm studying performance, what performance metrics? And these are the whole list of performance metrics. Especially, these are common, by the way, in cellular network. These are the performance metrics. So that clarity is so important. And look at the paper, how that's the beauty of this that I wanted to show you. Starting from beginning, okay, take a look at how it is written. Take a look to read it on your own in your terms. But more importantly, let's start with the model. Okay, here is our model. So system model. That means you are explaining the context, slowly introducing all these variables. Okay, for example, it is assumed that all base stations are equipped with a single antenna and transmit with the same power. That's our assumption. So we're not talking about multiple antennas, and the power is the same. So that's where how you're introducing one variable at a time. This is what I say, one character at a time. Okay. Okay. Then the other is, each user is equipped with a single antenna and is associated with the nearest base station. Nearest base station captures the traditional average received signal strength. And then service for each base station, the service area is geometrically represented by Voronoi tessellation, like in figure 2. So look at the presentation. Okay, I'll only highlighting few lines to tell you to point out how to write a paper. Okay, ultimately, okay. Yeah, ultimately, you are describing the received signal. Y, S is your intended symbol. S is the intended symbol. P is the power. H is the fading component, fading channel gain. R is the distance. R is the distance, and then you are using minus eta by 2. Actually, eta is the path loss exponent. Can you see the screen? Are you able to see the? So eta is the path loss exponent, and because you're dividing by 2 because you're looking at amplitude instead of power. Even the square root is coming because this y is an amplitude of the signal strength, not the power. Okay, and then look at this. The key thing that we are focusing is aggregated interference, and of course the noise. So this equation nicely captures in a very simple manner. It's looking at the channel gain and path loss, interference. All these are captured. Yeah. Yeah, actually here Okay. See, if you are looking at maybe the impact of environment and other things. Hmm. Hmm. Repeat that last sentence. Hmm. You know what? I don't think I haven't seen any paper so far. It's not included in this. So in fact, first of all, this is not about UAV. It's only about cellular. This paper is about just on the ground. But your point is interesting. I don't think at this point anybody has done that. But maybe we have to look into. I haven't looked at the literature very detailed, thoroughly rather. That I didn't find the things. Maybe I'm not looking for them. For this kind of edition, this kind of. What you're saying is the aircraft itself might cause interference, not like a structure, but more of conducting perspective. It's the first time actually I'm hearing, but it's a good point. Maybe you can look into that. So when you find that somebody has literature is not didn't include those kind of things, then you can start looking into that. Yeah, but this is simple. This model is simple, and even the papers that are on drones that are referring to this kind of model are simply looking at interference coming from other sources, not like the term that you use, conducting interference. I haven't seen that before. It makes sense. It makes sense. So I haven't seen really. So once again, I think my suggestion is, if you see something that is lacking in the literature, probably you should look into that. You may find something. It's not that you won't find in the, you will see, but probably there was no focus on that. There's not much attention. So the key thing that I wanted to bring is how to present how to start with a model for received signal strength. And keep in mind, we referred to in the previous discussion, we've seen the context, like how many, what are the interference sources of interference. Like for example, more specifically, when one UAV is trying to talk to, or one vehicle is trying to talk to the ground station, you are getting interference from the rest of the vehicle, because all of them are talking to the ground station at the same time. And we are not making any assumptions about what I call multiple access techniques. So we are not allocating, we're not using any scheduling. There's no schedule. There's no multiple access scheduling. Okay, then here is this is kind of interesting. Okay, there are a lot of other things that are discussed, but after equation 1, now equation 2 is explaining what the source of interference. How do you come up with a single term for aggregated interference? In fact, this is one of the key things that I want you to take away from this. We talked about how do you model interference, why it is important, but now we are actually getting to the crux, how exactly you do. So what this says is, so this is the desired signal, and this is the interference, and this is noise. So remember, we are not using log terms. This is not in decibels, right? So it's just everything is added. This is the received signal, a desired signal. This is a desired signal, but of course you have path loss and channel gain or fading is all included. Here also is the same term. If you look at the term is pretty much the same, right? Square root of P S H R, same thing. same power loss exponent. But what is this? Look at this. This is coming from all other Rk. Think of like Rk is a K is the all the neighbors which are causing the interference. Okay, K equal to 1, 2, 3. So those are the different vehicles that are present, or different users that are present. And then phi is think of set. Phi is a set of all those. R1, R2, R3 are all the elements of phi. And R0 is what we have desired. So by the way, what is R0? R0 is the distance of phone 0 or user 0. All other users are causing the interference. So all other signals except the desired signal, which is the first term, all other signals, all other users in that set are causing the interference. So it's pretty much the same, right? Not one interference. One term, you're aggregating everything into one term. One legitimate user, R0, 0 is the legitimate user, and all others in the set are users which are causing the interference, because they're all talking at the same time. We did the same thing with respect to drones also. We said there are several vehicles in the airspace, and I'm interested in, I mean, if you look at from the perspective of one drone, that drone is interested in talking to the ground, but all of the drones are also talking at the same time. So except for the 0, if you index the desired signal with 0 user, or index the drones with numbers 0 to n, 0 is our desired signal, but all others are interferent. So point I'm trying to make is, see how elegantly it is formulated. Okay? And notice this, in this set you are skipping R0, because R0 is the desired signal. R0 is desired. So if you remove R0, all other users are causing the interference. Same term, it's the same signal. Like the same thing, for example, I'm talking to you, Durga Prasad, right? So then I want to talk to Sumit also, or Sumit wants to talk to me later. But at this point, when I'm talking to you, Sumit's talk, if he talks at the same time, that is the interference. Same thing with everybody, every other student also will be like it. But the same model is the same, they're not going to change. Same model, same, the signal reception model is the same. By the way, where are you? Depending, you need also to say what, typically you also think about, is it downlink or uplink, who is the transmitter, who is the receiver. So in this case, I think it's clear from this formula that all of them are talking to one base station, and one signal coming from the what I call desired user is the desired signal, and all other signals are interference. And that's the point. See how nicely we are able to capture. Now the question is, how many are there? How do you know? That is where we are using the stochastic geometry. So remember Dr. Venka was talking about Borel sets, Poisson point process. So what is the ultimate thing that you can see? You're assuming some distribution. Basically you're saying the locations of the vehicles follow Poisson distribution. And then if you are, my question here is, how many drones are there in that area? How do you answer that question? Because you are using the distribution, you can define the area. If you define the area, you can tell how many drones are going to be there. See the beautiful connection from there to here. So this is only one example. That is the point I'm trying to, what I'm stressing is, by learning the fundamental concept that Professor Venka was teaching on that day, and you can use that mathematics for many understanding many more, developing many models. In this case, I'm talking about interference. Okay, our focus, because the focus I wanted to discuss interference in this series, so that's the reason I'm focusing on interference. But that doesn't mean that you can think about there are other applications too, other scenarios within the context of aerial networking. There may be other applications that other things you can study. But the question here is, the one question that we need to know is, what is the size of this set? And for that, you can use the techniques and concepts that Professor Venka was developing the other day. So that is the main thing that I wanted to cover today. Okay, so the key thing is, we don't need to go into a lot of other equations, but this equation is clearly telling you that what is the desired signal and what is the interference, how to model that interference, despite the fact that you do not know how many drones are there, but you can make a good estimate by using the Poisson point process model that we learned from Professor Vanka. And also the concepts of stochastic geometry also will be are explained here, but if you read the entire paper you will get the idea. So let's go a bit more. Yeah, so look at this paragraph. I want you to, let's go through this from two perspectives. How nicely it is presented, number one. Number two is how you are gradually explaining the variables. For example, the phi, we're talking about phi of xi. Xi represent the coordinates of the ith base station. So you have to be a little more careful. Now, are we referring to, in some cases, the same equation could be used for understanding the communication that is going within the one base station, or in fact, if you say phi is a set of base stations, then you are talking about interference coming from other base stations. So, but the formulation is the same. Whether you are talking about for one user, interference coming from other base stations, or within one base station, you are modeling multiple users within. So both can use the same formulation, but you have to read this before we interpret that equation. I suggest that you read this explanation to concretely understand things. Some of the terms that we talked about. So lambda is the intensity or density, for example. I think for the distribution. Then we are talking about R0, the serving distance. R0 is a random variable. So now remember that one of the slides Professor Vanka was asking, can distance be a random variable? That was the question, right? If you remember in the slides, one question is, can distance be a random variable? Normally on the ground, we know the distance, but here the scenario is, I mean, again, this is not about drones, but in our context, drones are moving. So distance is suddenly become variable because you don't know exactly what will be the distance. It depends on the mobility, right? Because mobility is random, so the distance has now become a random variable. So that is how he's saying R0. Yeah, somewhere here you go. Yeah. So I think you got the idea. Basically, we are justifying, when in Professor Prakash, that day, Professor Vanka was telling, can distance be a random variable? So here is the scenario, where in this analysis also, this other actually looks at R0 is a random variable. This again? Right, yeah. So in this case, because the drones are flying around, or maybe in our case, okay, this is applicable. R0 could be a distance is modeled as a random variable. Right. Okay, we won't go further because I just wanted to set this. We only got through two equations to explain how interference is modeled in this case, right? So give me. So we spent some time on interpreting this equation, showing that at the receiver, this is the desired signal and this is the aggregate interference. So the next question is, once you know what is RK, or if you can figure out how many, first of all, how many users are there, how many drones are there, in our case, then you can try to estimate this. So one thing is, you may know the what you call the number of users. You can estimate, of course, it's a probability distribution. From the power, you can estimate how many users are there. But more importantly, how do you know the distances? Because you need to know the sum of this term, right? So everything is other than power. If power is, you can assume that power may be fixed. Then hk is a random variable, rk is a random variable. So you need to come up with a way to find this sum. And let me jump into my problem now. So far, this one. Yeah, because I think probably, see, yeah, this noise. It could be, but yeah, that way. But probably, since we are looking at, I'm interested in only one receiver, like this is my desired signal. So this at one receiver, yeah. By the way, it's one receiver, yeah, for that channel only. All these yeah, right. You're right. So at the receiver, this is the desired signal, and this is the noise at the receiver. All these are interference. Yeah. Fine. So this paper strongly suggests everyone to review and understand the concepts presented in this, and it's a tutorial paper, by the way. All right. It's not easy, because it's a new topic, new subject. Okay, now let's move on to how I use this in my context. I'm going to show you two papers. Interestingly, I needed to study this interference in two research topics. It's still in progress rather. So one is in the discussion that the paper that I showed you before in the beginning, where the goal is to study the link budget analysis. So in this context, I needed to understand the interference. So how did I do that? Yeah. So this is what I needed to. In the given context, I wanted to study the how to figure out the interference. Each one is So look at how I try to do this. Okay? That's what I want to show you. You're still working on it. Yeah, but notice, I have talked to Professor Venka before, but interestingly, the locations we are assuming the PPP. And this section I worked on it very carefully and helped a student. He is undergrad student, the guy who developed. I gave him the idea, but he is actually undergrad. But what he does is he follows my instructions so meticulously, and whenever he makes a mistake, I'm going to fix. I fix this section itself took several days, several weeks actually. So this is our assumption. So once again, the goal is to model the interference. Okay? So then look at how we are building. Our goal is to design a framework for estimating the interference on the air to ground. So this topic is about air to ground. In the other topic, I'm using air to air. So this paper, link budget analysis, is focused on how many cell towers I need. So you talk about to provide or to figure out to analyze the communication system or build the communication system and analyze it in the context of air to ground or ground to air. And the other paper that I talked about, I'm going to bring up that again, air to air. So the context is very the contexts are different. So in this case, yeah, US are flying only within the context. This is one restriction that allowed me to simplify. Otherwise, yeah, you can do simplification even in other contexts also, but this becomes much more practical. So we're saying you're not, all the vehicles are not everywhere in the 3D space, but they're only flying in context, designated context. That's simplified. Second is we are not assuming that there are no other vehicles. Only drones are. We are not allowing. We are not assuming. We are not expecting any other truck. That's also reasonable because in future there will be designated corridors. The only place where you cannot expect defined space is when you are going up and down. When you are climbing up or climbing down, you can assume you cannot expect free space. You can expect other. But typically, we are assuming that once you design develop this corridor, only drones are. So for example, maybe on the roads right now, both self-driving cars as well as manned cars are also there. But in future, probably at least for the airspace, this is possible. There is no assurance that we have dedicated. That's assumption B. So these assumptions have to be laid down very clearly. Otherwise, you get confused. Then you're missing it. Then all UAS are maintaining a minimum safe distance. They're one directional. The locations are filled. And then model parameters. These are the things that obviously low density is an important thing. Noise power, interferences is only variable, but I'll show you how we are computing. Yeah, now coming to exactly the focus of our talk. Interference is the total power the received signals coming from all UAS other than the UAS that is communicating at present with the ground. We're saying we're not assuming any sort of multiple access technique, no scheduling, and then only one vehicle is important at a given time. So we are interested in making sure that communication is given importance and all of the signals are. Then all of them cause interference. The higher the load density, the larger is the. So now look at the main thing. What we did is let D bar represent average distance. Let D bar represent the average distance from any UAV to the this. My goal is to figure out average distance. So D is like a random variable. Okay? So D is a random variable, but in fact, to some extent, in my case, it's sort of not totally random. In the sense, when you say that the drones are all flying at one altitude, to some extent you are restricted. The height, at least the H is fixed. Height is fixed. Right? But then they can be anywhere in this. The altitude is fixed, but the horizontal distance is not fixed. Vertical distance is fixed. So, but in general, yeah, it still right now on the resume it's still a random variable. But what is my goal? To find the average distance. So I need only one term. I'm not concerned about individual distance, but I need only that. So for that average distance, we came up with this formulation. What is this? I'll quickly describe that average D. First of all, you are looking at the length, width, height. Length, width, height of this corridor. Remember, corridor is now, you can think of a rectangular. But it has a L down, length, height, and height. So that's the average. You're dividing by the volume. Basically, you're dividing by. And here, these dimensions are 0 to h because the h is positive. But then, if the width is, of course, you can say 0 to w or minus w to w. So w is the width, L is the length. So this formula captures the average distance. So now suddenly the problem becomes simple. Once you It takes probably a few minutes to digest or understand this stuff. It's common. But once you have D, look at suddenly how the signal to interference ratio becomes simple. So what we are looking for is what is the desired signal and what is the interference. So what is the desired signal? P, which is the same for every drone. So think of this: a lot of drones are there, and each drone is trying to communicate with the ground control station, and one of them is what we are interested. One is the desired signal, but power is the same. We are assuming that all drones are talking using the same power. So PU is the same for everything. PU is for the desired signal as well as for the interference. Same. I use the term GU. GU is the product of transmit gain as well as receive. So you can ignore that, but for generality's sake, we use the term G. Instead of writing GT times GR, we just say G. Is the product of G. And what is HUN? Is the fading channel gain, fading parameter channel gain. For the user, you are interested in what reference or desired result, okay? Desired growth. And D power alpha, this is the path loss estimate for the desired zone. And let's look at the interference. This is the noise power. And interference is coming from all other users except the desired. So every signal coming from everybody else. It's the standard. The key thing here is we're trying to simplify. Suppose there are n number of drones in the airspace. All we are looking for is the average distance rather than schedule. So basically, you're saying you're using some sort of a distribution. But here, if we don't simplify, like if you don't have an air corridor model, then drones can be everywhere in the 3D space. But that is simplified for us in this case because we're assuming that you're defining the corridor, the number of drones are limited, but fixed like n. And that depends on density. So if you can say depending on the density, you can estimate how many drones are going to be. Yeah, so I hope you have made the point. So starting from here, we went through some basic assumptions, and we use the interference. We use the signal to interference formula that is commonly used. Then I try to figure out how to estimate the interference in the most simplified sense. Okay. Now that's failure, and then rest of the things are in terms of simulations. You can start giving some model parameters, assign some parameters, and start. My student has done all this. So for example, we looked at what will be the free space path then received power versus distance, then again SNR, data rate, all those things. So this is one. The second thing is also what to show you, even though I briefly discussed that in one of the previous lectures, it's about air-to-air traffic. So here this is about air-to-ground. In both cases, drones are flying in air corridors only. Our the vehicles are not totally randomly placed. They are placed they are not everywhere in the 3D space, but the drones are flying. Or positions of the drones are limited to only that corridor. So that puts some sort of a restriction or a bound in terms of estimating number of vehicles. It gives you a little more control. So otherwise, it's okay. We can still say we can use the point that the ideas that presented by Professor Venkat to estimate. All we need to know is how many drones are present. Number one. Number two is what is the average distance from the drones to the ground control station. Okay, so it becomes a little more challenging, of course, to find the average distance given these locations the drones are more random than compared to restricting the drones only to the air corridors. So after that we can wrap up, but but let me show you that paper as well. In fact, we use the same ideas, but it is the model is a little more tractable. Okay, so I discussed this before. I just wanted to go through it quickly so that how the context changed. So in this case, focus on, ignore this part, okay, just focus on the interference part. So our work starts from here, the right side. This is what you are interested in. Once again, the goal is to estimate data rate, communication range, and SINR. And more specifically, this is where we are. This is our goal. This is what we want to study. So in the case of SINR, once again, we start with node density. Let's assume node density is given by lambda. Then we fix the volume of airspace that we are interested in. It's like a rectangular prism where length, width, and height are important things. And then what we said is, this volume is for one unit air cell. We introduced the term of air cell, and the corridor is a set of air cells. Okay, if you limit to 2D, this is how it looks like. Each one is a cell. This is 2D, but in our case, it's a 3D. Like all these cells, one after the other. If you put in a sequence, that becomes our corridor. And then lambda is very simple. In this case, 1 by V, because why is that? We are restricting to only one drone per cell. So one drone per the volume. So that's how lambda could be explained. So this is much more tractable. See, it's not totally random. It was in Poisson point process. The distribution is more truly random. But here it's not completely random. You are restricting. There is only one drone per cell. So it kind of simplifies. So you can see the calculation actually gets much more simplified, because same idea, same term that you saw before, same expression, desired signal and interference. Desired signal in the numerator, noise power plus interference. That's basically SINR. So both in the air to ground model and air to air model, this is what we are focusing on. And how do I get the interference? Average interference. All you need to know is average distance. See, what we are saying is we are aggregating. We want to find aggregate interference, right? How do you do that? In this case, we're trying to find what will be the average distance, average of all distances from every drone to the ground control station. Sorry, it's the other way. In this case, air to air, right? So we're taking average distances from every drone to the receiving drone. So let me give a little more concrete example. Let's use this, like this is my corridor. Let's assume there are 10 cells, and then one drone is talking to other drone. Say first drone is talking to the last drone, and then so at the receiver is in one location, or in this case, let me be more specific. Say I want to give you the context a little more clearly. Yeah, here you go. Consider a scenario in which a pair of UAVs are talking. So you're saying U1 is talking to UN. UN is the receiver actually. The receiver is at U1, the transmitter is UN. So in this case, if you assume 10 cells, the 10th cell is the transmitter and the first cell is the receiver. So there is a drone in the very first cell which is acting like a receiver, and the drone on the 10th cell is talking to the drone in the first cell. So again, this doesn't restrict the generality. The concept is, even though you are fixing the transmitter and receiver, it's a general model. It doesn't restrict to only that locations. But the main point is, how do you find the average distance, average of all distances from every other drone, or every drone rather, to the receiver. So once again, the receiver is in 1. So what we need to know is that what is the distance between the receiving drone, the receiver rather, receiver, from first the drone that is in the second cell, from the third cell, from the fourth cell. So what is the desired signal? Desired signal is the signal coming from the last, the UN is the transmitter. This is what we are interested in, and all other signals are going to be causing the interference. So our goal is to find aggregate interference, the aggregation of all the interference coming from all other drones except the legitimate or desired transmitter. See how the problem becomes simplified now. And we are also putting a restriction that in our corridor, only one drone can be there. At most one drone, at most one drone can be there in each of the cells. Yes. Okay. Yeah, actually this is all done. It's already in 5 minutes. So we will be done, and then so problem suddenly became much more simpler and tractable. So I also assuming, like, let's look at the worst case analysis. Worst case analysis is every drone is occupied with drones, but since there can be only one drone in each cell, so at most the worst case, if there are 10 cells, there are 10 drones. If there are n cells, there are n drones, and out of them, one of them is one of the legitimate transmitter, and one of them is a legitimate receiver. So everything else becomes the interference. Okay. So with that, the same term becomes much more tractable. Yeah. In corridor, 1, but we look at the worst case, which means that every. So if there are n cells, then there are n drones, and out of them, one drone is talking to other one. So that's the desired signal, and the remaining drones are causing the interference.
Because I have been trying to understand. Because in our earlier sessions, we were discussing like there is a possibility of some drone in the other corridor enters after the.
Yeah, that's it. But in this case,
all these values get changed.
Yeah. For now, it is corridor. Yeah, but in this case, just only we're assuming only one corridor, not thinking about multiple lanes and all.
Depending on total coverage area to be covered by the number of drones will be fixed. Like, because we were mentioning earlier, to cover the entire zone, we will be trying to estimate number of drones.
Yeah, same context is applicable to here. What we are saying is, okay, there is a corridor. Like, for example, you have designated a route from Warangal to. So let's call that as a corridor. And truly speaking, the corridor is okay, like a rectangular principle. For academic theoretical purposes, we do. And then we are defining the corridor to be a series of cells, right? And then you are trying to provide communication support through base stations placed on the corridor, along the corridor, but on the ground. Right? But in the previous paper, we looked at air to ground communication. But we are looking at when you are communicating and one drone is talking to the drone, what will be the interference coming from the rest of the drones? Just the contact. But the problem is, the point is, you simplified this interference estimation by making these assumptions, even though it is a purely random, the locations are random to begin with. In this context, interestingly, the problem becomes much more simple. That's what I want to say. Remember, we began this lecture with the idea of Poisson point processes, which you learned from another person. Obviously,
the worst case conditions where all drones are there, are only one and one.
Yeah, but here we simplified the framework to specifically one air corridor. Then we also put in further restriction that that there are series of cells and there is only one drone per cell. So that made the problem much more tricky. I think that's the main idea that I'm saying. On one hand, we're talking about Poisson processes to figure out where the drones are located. Randomly distributed, but you are assuming that they are follow the Poisson distribution for the placement. And then we talked about aggregating, the need for aggregating the interface using stochastic process, right? But then when you impose a specific structure like air corridor, air cells, then the problem becomes much more tractable. And what is our goal? In all this whole lecture today, the goal has been to study this term. What is that? What is the interface? That's how we did. How to estimate the interference, that depends on the context, the problem, and then on the model definition, the scope of the problem. Then if everything is done right, then your estimation of the interference becomes more reasonable, more accurate. Yeah, that's something. So what happened is we needed to find average distance. So what are the distances we are looking at? What is the distance of from second drone to the first drone, and then from third drone to the first drone, fourth drone to the first drone? Because there are drones in every cell, and the drone in the first cell is a receiver, and drone in the last cell is a transmitter. In between, all the drones are talking because they're all actively communicating with something else among themselves. But our interest is, our desired signal is the signal coming from last drone to the first. That is the desired signal. That is the numerator. The signal we are looking at signal to interference, signal to interference plus noise. That's the term here. So our goal is to figure out the I aggregated interference. And then for that we wanted to say what is the average distance from all the interfering nodes to the receiver. So receiver in the drone in the location 1. So every other drone is calling the interference. So what we needed to do is we needed to find the average distance. So there became a summation, right? 2 to 1, the distance is 1. 3 to 1, the distance is 2. So suddenly it became 1 plus 2 plus 3 plus 5. So the summation is n times n plus 1 by 2. That's what it is. Suddenly it became a simple sequence. Once again, because that's the model that we are looking for. First, L is actually the distance between cells. So anyway, this work is still in progress. So in fact, what I presented to you is understanding the interface. How do you model the interface in different terms? In one case, get to ground. Other case is into air. So I hope it made sense, especially the graph. We started with 2 beautiful papers. I think Madam Anuradha will know when I say Aluni. Aluni is a very famous, very well-known researcher. He wrote the paper on how to use stochastic geometry for problems related to cellular communication. So that paper, not only that is a very experienced professor, but the way he writes the paper, every paper is so fundamental. And that is how when the time comes for you to present a write a paper, it has to be written like basics, easy to follow. At the same time, go deeper. So that's one thing that we talked about. Okay. And then we also connected whatever we're discussing with the presentation done by given on Saturday by IoT professor. He also emphasized, he's also studying Poisson process. And then I connected them to 2 different projects that I am working on in the context of airborne networking. One is air to ground and one is air to. And again, all these works are
Sure, we're done with that. We're completed. Okay, then we can meet in the afternoon around 2:30. Right. Now we will proceed with the faculty members of the department. One will join, but the meter said. Good afternoon, all of you. Today I'll be giving you a 1 hour lecture on long range communication. Last time we have done short range communication. What are the technologies available to us for range communication? And the another important thing is, can the existing technologies what we use on terrestrial can be directly used for non-terrestrial? Or we want some other new technologies for that? We try to explore it and we try to see what are the present technologies, what are the options left with us, and how to go along with the new technologies. So this is again just trying to review back. We are trying to look from the long range protocols or the existing technologies what are there, and we try to look for the next type of technologies what we can venture into it. So when we are trying to look for the long range communication, the spectrum or the frequency bands what we are trying to use comes under two bands. One is licensed, you have to pay license and you have to acquire it. The other one is unlicensed form. So this circle shows that it is the unlicensed spectrum or the technologies available, and this is the licensed spectrum what is available for us for commercial purposes. So all these things are long range only, but these are unlicensed and these are licensed version. So in the licensed version, if you try to see, the popular one is the cellular networks, where we pay some amount and use the spectrum whenever we want it. Or you can have a totally a sub-band of the spectrum and you can use it for your private purpose. We call it as private networks, right? The spectrum belongs to a service provider. For example, in India, we have Airtel, Jio, and so on, Vodafone and all. We buy some spectrum from them and we use it for our application. So if I have industry in 3 or 4 places, I can use the spectrum connecting all the 4 places together. We call it as private networks. It doesn't mean that private networks is owned by a person. It is owned by a service provider. We are taking it for rent and we are using for our purpose. So we have cellular networks, and the other class is low cost, low power networks like LoRa, low PAN, low power WANs, low PANs we call it as, and so on, right? So now, under these two licensed and unlicensed spectrum, if we try to see, in the unlicensed one, and we are trying to look larger like 1 kilometer, above 1 kilometer and so on, not less than 1 kilometer. It is almost equal to 1 kilometer or more than 1 kilometer because we want a long range communication. So when you're trying to look from that, we have in the unlicensed low power wide area networks, we have MIOT, LoRa and Sigfox. These are 3 standard technologies which are being popularly used in worldwide. You can say worldwide. Sigfox is more popular in North America. LoRa is more popular in Europe and even America also. And MIOT is again a standard which is popular in some of the Asian countries and so on. And coming to license, we have LTE-M, ECGSM, and NB-IoT. And apart from these technologies, we have cellular 5G, 4G is anyhow we are trying to reach to the end of 4G and we are moving towards 5G. And the next step is 6G. right? And this is given by the source of that diagram is given over here. And please remember that when we are trying to look at the speeds, you also have to look at the data rates what you're trying to get, because the communication depends on the data rate also. If the data rate is so, the latency tries to increase and so on. So you have to look at the data rate also. When you're trying to look at a higher data rates, for example, if we assume that the 8 taxis are available, right? So the person who is sitting over there, he might want to watch a movie, right? Or he want to hear a song, or he want to play some game inside the taxi. Because if you're traveling in a bus or taxi and all, you want some entertainment. It is not that you simply tie your hands and legs and sit there and get down over there, right? So when we are trying to look from that end, the data rates also plays an important role, because the user or the customer wants some more comfort out of it. When he pays 1,000, he says, I'll pay 5,000 more, you give me some more comfort, right? Or sometime he might say that, okay, when you're giving me a seat, why can't you give me a relaxed seat so that I can spread my legs and sit? Because the time taken from here to Hyderabad is 40 minutes. So you want to relax for 40 minutes. It doesn't mean that he has to sit straight like this and with tied hands and legs and all. So the comforts comes in once the technology is available to them. So when we are trying from that end, then you have to look for your data rates also. It is not that the data rates are IoT is only a few kilobytes, so I'll design with that. You can start designing with that, but later on we have to see that whatever the customer needs, we have to satisfy. Otherwise, the technology will not take a shape, right? If you put a taxi drive as something you pay 1 lakh from here to Hyderabad, nobody uses it, right? So if you say that, okay, it is 5,000, people might try for it. If you say 1,000, everybody might use for it, right? So these are some of the things which we have to keep it in our mind as the technology advances and as the time improves, people might ask for more and more data rates. So in that case, if you are trying to look from that point of view, you can see that the cellular is a good option where you get a higher data rates than the unlicensed spectrum, right? So now, what does it tell us? It tells us something more interesting, like I have 2 types of data which is coming out from my vehicle, like drone or whatever it is. There are 2 types of data coming out. One is used for control of the environment. One is for user data transfer, right? When we are trying to look from data point, you have control signals and the user data. So the control data should be as small as possible, whereas the user data should be large enough. If you want to send an email, you need some space for that data to sit into the packet. Whereas if I want to control something like, say yes or no, the distance is there, or the temperature is there, that I need so much of space, right? So now, the new ideas like, why can't we combine technologies, one for control, one for data transmission, right? So these type of things can be like hybrid technologies can be used for, especially for the air or the drone technologies. One, you can use it for device-to-device communication. One is for user-to-user communication. So when it is coming like that, you can think of something like for device-to-device communication where it is less, you can go on with this, and when the data rates are very high, you can go for that. For example, if you try to see, most of the mobile companies, what they do, if you are using a prepaid, you have one tariff. If you are using postpaid, you have another. Whereas prepaid, the number of voice call is fixed. Whereas postpaid, they'll give you a lot of options because you are giving a larger bill for them, right? So this type of idea should be there when we are trying to look for the drone-to-drone communication. Mostly it is like we are trying to see from the communication point of view that there is a essential communication, there is a entertainment communication, right? So that's what we say, that hybrid type of technologies have to be looked at. And this we have seen it already. Whenever we pick up a network for a given application, we have to be very careful to see how far we can able to communicate, right? How far we are able to communicate is one, and what should be the data rate for communication, and then power, and then the frequency and security. These are the main important issues what we have discussed. Even for short range or for long range, they plays an important role, right? We have to look at the power consumption when we are driven by batteries. Especially we have to think about the power, and if you are thinking about the entertainment point of view, you have to go for a data rate, and the communication, how far you can communicate with your base station and all, which plays an important role. Or drone to drone, how much is the distance, plays an important role. And you have to see a frequency so that the interference is minimum, and the security. So here, the another important thing is frequency. When we try to look from the cellular point of view, there are set of frequencies which are given to a cell, and the same frequencies are not used in the adjacent cells because we want to minimize the interference. So when we are talking about interference, we have two interference. One is co-channel interference, another one is adjacent channel interference. So the frequency allocation schemes are something like that. When you give F1, you don't use F2, you use F3. And you don't use F4, you use F5, so that the adjacent channel interference can be reduced. And co-channel means, in this cell you are using F1, don't use F1 in the next neighbor cell, right? So that is what we call it as co-channel interference and this adjacent channel interference. So you distribute the frequency such a way that you try to minimize the interference among the set. Okay. So by doing that, what we are trying to do? We are trying to reduce the number of users in the system, right? If you remove odd numbers and keep even numbers, the total band has been divided into half only, right? And if you take a hexagon, there are 7 cells, you divide the 7 equally, then you see the number of users are decreased, right? So you have to come up with a new frequency allocation schemes such a way that they don't interfere. So what are that? You can pick up orthogonal number scheme and use it so that they don't interfere with each other. It is not just by arranging F1, F2, F3, F4, F5, F6 and so on. You have to use some different schemes so that the interference can be minimized, right? And here, even in the case of drones also, we try to see that interference has to be minimized. So what we do, we allocate different frequencies for the inter-zone communication, and similarly with the base station also. So any problem? No? Okay. So then the securities are the important. Securities also plays an important role, because there might be rogue drones, you might be trying to jam your signal. Jamming the signal is not a problem because communication will not happen. But security, if a wrong signals are given, then they try to coordinate with a wrong drone and get a wrong information. So it says that nobody is on the way, but there is something on the way, they go and hit it, right? That can be one of the reasons. It is not that always it happens. So there might be a rogue drone which is saying that there is no object in front of it, because it's a cooperative communication. They cooperate among themselves for cooperation. And when it gives wrong signal, it go and hit the other object. Or it may say that, okay, there is somebody in front of it, it takes a deviation from that and it goes in some other direction, right? So we want a secure type of communication so that the rogue drones or rogue information can be removed out of it, right? So the security mission is also critical, but at the same time, we should also see that the energy consumed by security algorithm should not be too large, right? So we need some good techniques like, for example, if you try to see IoT device, we use Eclipse type of security algorithms and all, where it takes very small computation number to find to secure the communication and all. So again, in the last class, this paper, Swaim and Chaudhary, if you try to see, they have given a connectivity for the IoT device, because all the device they assume that it is IoT only. Even it is a drone or it is a balloon or it is a app, whatever it is, they are IoTs only. They are not manned by, there is no person who is trying to man it. Unmanned vehicles, we refer it as IoT. So they have created a good diagram which gives a lot of idea. Like they separated the cellular part and the non-cellular part. They have not defined apart the licensed and unlicensed, but they call it as secure, the cellular type and non-cellular type. And they have given in this, there is a provisioning and licensed type, and there is a non-cellular, you have a personal area, or you can call nano areas, and LAN, wired and unlicensed and satellite and so on. So in this, we also have given a lot of options for us, because most of the non-cellular, we consider it as an unlicensed band. Okay, so they have kept all these things as an unlicensed one. You can just use it, buy and use it. But as it comes to satellite, it is not to just use it. You have to pay for it, right? And now, the same slide we have seen in the short-range communication, but when we try to look from the technology, what we are trying to look at, especially the Sigfox, if you try to see, their range is around 40 kilometers. And the NB-IoT is around 10 kilometers. The LoRaWAN is about 20 kilometers. So especially the down ones, if you try to see, they are for a long-range communication. Minimum of 10 to 20 kilometers are there, right? And the data rates are also quite reasonably good for device-to-device communication, or the control information, not for messaging purposes, right? And most of them are used under unlicensed. Only the NB-IoT has a licensed spectrum, whereas the LoRaWAN and the Sigfox, they are working in unlicensed bands, right? And you can see that they have a different frequency, which we are not using in India. We have only 2.4 and 5 gigahertz as unlicensed band, whereas here they have 868 and 915. 868 in Europe, 915 in North America, 433 in Asia, right? So still in India, we have not opened up 433 megahertz for communication, right? And this is right now under defense, and they have to clear it for the purpose and all. It takes some more time for getting that as a free band. Okay. And here also, if you try to see, the same frequencies are used even for Sigfox also, right? So the LoRa's, what we are getting right now in the market is trying to operate at 433, but we cannot use it for a long distance communication because it is not unlicensed in the case of in India. Okay. So the power consumption is also very less, if you try to see, because for driving the signal for 20 kilometers or 10 kilometers, your power has to be very high, like 2 watt or 4 watt or 5 watt, it should be there to drive it. But the power wattages are very small in these cases, and you can see the currents are only milliampere currents we are trying to use it to have that. I square R is the power, so you can easily calculate the power. It's square of milliamperes only. Okay. So this is one important thing. And the another important thing what you try to see is they are heavily secured with AES 128 encryption bits, 128-bit encryptions, right? And it is good enough for the communication purpose. By the time you decode it, the communication is complete, right? And in the last class, we are trying to see the Wi-Fi networks are trying to sit on the cellular network, or the cellular networks are sitting on this Wi-Fi and trying to download most of the traffic into Wi-Fi networks, and they are trying to communicate. This is another important feature because in the terrestrial networks, we are trying to release the spectrum of 5G for other communications, right? We have to view from that point of view. Like most of the 5G data are shifted into Wi-Fi, and the 5G spectrum is available to us so that we can accommodate new users into the system, whether it is drones or HABs or balloons or something. We are trying to push it into 5G, and the terrestrial 5G is being pushed into the existing Wi-Fi networks. So now let us look at each one, starting from unlicensed to licensed and cellular. We'll try to go it. And coming to the licensed, if you try to see, in most of the cases in licensed spectrum, we have three options available to us: LETEM and ECEGM and NB-IoT. Right? So these three are available to us in the licensed low power wide area network. Okay, we want a long distance communication and it should be low power. And that in that technologies, if you try to see, we have three options with us, existing options, which we can use it for a communication purpose. And one is LTEM, long-term evaluation M for machines. And when we say machines, it can be any machine. It can be a lathe machine, or it can be a fan, it can be an automobile crane, it can be a drone, whatever it is, right? So here, if you try to see LTEM, it has a low power wide area net technology available for it, which means that if you try to see the device, the battery, as long as 10 years it can work. You put a small coin battery into the system and you can use it for 10 years. That's the meaning of low power wide area network means. The power consumption is very small so that you can drive it up to 10 years, because you have seen milliamperes is the current. So if you try to take a battery which is around 2300 hours, then that will count to how many hours you can give on it. Okay, and the beauty of this LTEM is, as the networks are also LTE, long-term evaluation only, 3GPP networks, so you can use along with that technology. You need not have to have a separate network. The same network we can put in this feature so that it can connect all the machines to it. And the life is around 10 years. Once a machine is operated with the battery, you can use it for 10 years. That's the meaning of it is, when we are trying to use some devices at the border or somewhere, we cannot go and every day charge it. We put a battery and leave it so that the device can exist for a longer period. And we can get these signals from. So mostly what we try to do is, in electronic warfare and all, we just lay those devices inside along the border. So when some activity is going on, like people crossing or something is, soldiers are marching or vehicles are moving, it can be easily monitored. And the distance is also large. It is not few 100 meters and all. It is around 5 to 10 kilometers. So you can stay away from border for a longer distance and observe all the activities what is going on. Right? And we'll see the non-terrestrial networks a few minutes later. So there also we need this type of technology. It is not that only defense and all. There are a lot of civil applications where we try to use such type of technologies. Okay, so the only advantage is it can coexist with all the mobile technologies, and it supports low device complexity. It can support high device complexity, like it can be connected to a bulb, it can be connected to a lathe machine where there are 10 or 20 sensors, it can connect to a car where there can be 500 sensors and so on, right? And it has both type of coverage, even indoor and outdoor also, right? Even indoor also, if you try to connect some of the devices, they can be communicated and so on. Outside also it can be connected. Okay, so this is prime important to us. And the other things are ultra low device. These are all only for saying that the technology, when you try to compare with two, you have to use those parameters for comparing. Ultra low device cost, low device power consumption, and this is nothing but equal to your 10 lakh battery set, right? So this is one advantage. What you can see is the device, you can connect large number of devices, because you need not have to have a separate infrastructure. The same mobile network can take all these things, and the lifespan is 10 years, and you can connect peacefully some few thousands of the device together onto the network. Okay, and there is a good security feature incorporated where you can use the user identity, and you can also authenticate it. You can put a login and password type of authentication. If it is not login and or OTP based or some code based authentication, integrity and mobile identification, equipment identification. This is prime important for us in your drones. We have to identify the equipment and then try to communicate. So just the other two, if you try to see, EC, GSM and NB-IoT, this is also from this paper only. So you can see that the GSM, which means that what we have earlier, the GSM network, 2G network, what we have, can be used for the connectivity purpose, which means that the infrastructure what is there in the 2G network, they are lying idle, they are not being used now. So we can use that structures still to communicate, because if you try to see the GSM 2G network, they are run at 900 megahertz bandwidth, right? And presently the bandwidth is, the frequency is 2.1 gigahertz and 5 gigahertz, right? So the advantage over here is when you go for a lower frequencies, the wavelengths are long. And when the wavelengths are long, the object size and the wavelength plays an important role in the signal transmission. So as the wavelength is large, it can penetrate through the objects. And if the wavelength is getting shorter and shorter, it cannot penetrate through the object which has length more than the wavelength, right? So with this, you can see that 2G can penetrate into a house and go through, whereas the 5G signals or the 4G signals cannot come inside the house, because the objects are very much larger than the wavelength what it has, right? So when we are trying to go to a lower, that's why you can see that 433 has been picked up by most of the time. As you go lower and lower, the signal can penetrate through the objects to the end, right? So as the technologies, if you try to see GSM, they have 900 megahertz transmission. So at that, the penetration is high and it can go for a longer distance. So that's why when we are trying to use the existing infrastructure, what is there with the telephone suppliers, if we use it for drone communication or some communication, it might be cheaper than installing new base stations with new technologies and all. So this is what is called as extended coverage GSM. We are extending the coverage of GSM for the application purpose. Okay, so it is based on low power wide area technology, based on general purpose radio services. This is 2.5G, we call it as. GPRS, we call it as 2.5G. From 2 to, we have moved to 2.5, where it is packetized and sending it. So, and this has a high capacity, which is almost like twice of the 64K, it is 128K bits you can transmit, or higher also, you can, with better coding. Long range, low energy, low complexity cellular system for IoT. So this is the another advantage what we have. The infrastructure what is there lying can be still used for our communication purpose, for having a long distance, high capacity, low energy applications. So the next one is narrowband IoT, NB-IoT we call it as. So this is again a standard low power wide area network, and which has been developed for these wide range IoT devices. Like for example, you have a street lamps on the road. Every pole you need not have to connect with wires or some technology or not. So if you have a transmitter, you can connect to all the IoT devices directly. And this is another good example for, I think I might have told you, for the energy meters what the smart cities are trying to install. All the energy meters will be connected through the narrowband IoT technology, or LoRa also. Nowadays people are trying to LoRa. So they try to connect it, and meters will not be there. Small unit will be there at your house, which will be trying to communicate the signals to the exchange, or the distribution center, or to the energy office, and they generate the bills for you, right? And most probably by, I think by this year end or next year, we'll have prepaid energy meters installed, right? Which means that you put money, use it, as and when it is over, you again put money, use it, and so on. So the plan over there is to reduce the misuse of electricity and stealing of electricity. They want to reduce this part and try to go for these energy meters. And some people say that I got a long bill, so I will not pay and all. This type of things will not be there. As you want to use your mobile, you put your money and use it. Similarly, you put your money and use it. And here also they are claiming around battery of 10 years. So if they put that unit in your house, that can withstand for 10 years, which can be used. So now let us have a comparison of these technologies, because that will help us in understanding much better than we say some discrete things. So the source is again the same source, and you have LTEM and NB-IoT. If you try to look at these two, you can see that the bit rates, the downlink peak rates, if you try to see, all are in MBs, whereas here in KBs. That is one important thing which you have to remember. If you have a larger data to be transmitted, then you have to go for LTEM. If it is a very small data, so you have to communicate, it is NB-IoT is sufficient, right? So the major difference comes in the communication range, rates, data rates, right? And if you try to see the uplink also, the data rates only will tell you. When you have a lower data rate to be transmitted and capture it, the NB-IoT is good enough. But if you have a higher data rates to be exchanged between the device and all, you have to look at LTEM, whereas NB-IoT is not an option for you, right? So that is one good important takeaway. So the next another thing, if you try to see, the latency is almost same. They are not much different. 10 seconds. Oh, sorry, this is milliseconds if you are having this CAT-M, but here it is a larger one. It is going up to 10 seconds, right? And the number of antennas are uniform. There is no much difference because you are using only one with omnidirectional antennas and all. And you have a duplex mode, like you don't need two set of frequencies for up and down. And you can use the duplex mode, full duplex and half duplex is there with all the LTEM, but only half duplex is there in NB-IoT, right? So if you try to look from this point of view, all these parameters trying to compare, the device transmitting power is almost identical. Both are transmitting same power, but the data rates are very small in case of NB-IoT compared to LTEM, and the mode of transmission, this is half duplex, whereas you have both half and full in the other case. And the device bandwidths are smaller in the case of NB-IoT, whereas you have a larger one in case of, okay? So now we have to make a decision which one we want to pick up for a application, right? So this tells clearly like the device power consumption is almost identical, but in one case you get a higher data rates, one case you get a smaller data rates, right? So now coming to mobility, because we want mobility in our device, it is not stationary kept somewhere, they are moving. So now that also plays an important role, which technology we have to play, because in the earlier case, if you try to see, there is no mobility factor over here. We only compared based on the technology only. When we want to use it for mobility, because the device, the aerial drones and all are moving, they are not stationary. If you want to look at it, NB-IoT does not support handovers, right? From one cell to other cell to other cell, it cannot hand over that. The technology doesn't support that. So when the device starts to move away from the base station, the device continues to stay connected by increasing the transmit power as much as possible. Whatever it has, it tries to keep in touch with it. Once that situation has crossed, it has to break it, right? So that is one important feature which you have to keep. It doesn't have any handover process to move from one station to other station, and hence we have to be very careful in using NB-IoT when there is a mobility in the device, okay? When the device is out of range of the base station, it disconnects and tries to connect to the new station again. So now, when it tries to do that, it is something like a hard handover. You break and then connect. It is not that you connect before you break, right? So you can do that option when the other base station communication range and the previous base station, they are overlapping, right? We can still have a handover process by some other mechanism, not because the base station provides that, right? We can do that by some mechanism where we can connect to the other base station, but the call cannot be transferred because the base stations are not talking to each other, right? So the implementations also we have to see. We can do that, but it needs a lot of redoing the things again. Okay, so whenever it drops and connect again, it has to consume lot of process or the power it requires. So when we are having to hand over the process and all, we can do it only by breaking the first connection and reconnecting to the second connection and all. Okay, and if you are moving at a higher speeds, then the time left for you to do the job is very small and it might permanently cut the call. Whereas here, LTEM supports handover operation by communicating with one or more base station and try to establish the connection. So you will not have drop-off call and all as you move along. So when your devices are moving with a faster rate, then better to go for LTEM rather than NB-IoT. Like for example, you are walking from one cell to other cell. Vehicle. You can do it. That's what we call it as. We call it as cell drag. Cell exactly will not cut. Cell will drag for some time, like the signal will drag, right? We don't have a perfect cut line and all in the cell definitions. So you have a cell drag. So you have time to do that. And that is possible if your mobility speeds are very low. If it is high, you will not be able to do. Yeah, you can still have the call continuing. That's what I'm saying. If you're walking slowly from one cell to other cell, the call can be still there because the time taken for a handover process, dropping and reconnecting is very small. So if you can walk that much slow, you can still be on the line. If you're moving fast, because the velocity of the drone is a little bit faster than what we walk. It's not a little bit, it's more faster than what we walk, right? Because they'll be flying with 100 kilometer per hour or 80 kilometer per hour or 60 kilometer per hour and so. They are not walking slowly like what we. That's why you can see that even if you are outside the cell with a mobile phone and walking, the cell will drag. That capability is there, right? Boundary? Yeah, that is not the limit. Actually, what we say is the equation is constant. Fritz's equation is constant. Power received is power transmitted into 1 by d square. Everything is same, right? So the PR, what you are trying to receive, should be your mobile should have that much PR to accept it, right? If your mobile sensitivity is too good, you can go for a longer distance. See, the PR, suppose you say 50 dB is the PR threshold value. If your thing is much higher than that, you can still receive it, even if you can go for a little bit more, right? Yeah, power only. If your receiver is too good, it can receive still lower signals, you can go for a longer distance. If it can receive lower, you can go still further distance. If your mobile is not good, then your coverage will be decreasing, right? So now, if we try to see the areas where these two technologies are available, the pink color is the where you have LTE and NB-IoT available to you, and this is again from the same paper. The pink areas where you can see you have both LTE and NB-IoT. right? And if you see, only NB-IoT is this place. We are living over here, right? We don't have this option of LTE and NB-IoT. Okay, you can see that this most of the Asian countries we have blue only. We don't go for LTE. Okay, and the pink is especially you have all the two options, and the Mexico and that side borders, if you try to see, they have only LTE-M. They don't have NB-IoT, right? So this tells you a lot of idea where they exist and where don't they exist. So you don't have an option left, right? Okay. So this is, I willfully kept it because to make you understand that where two technologies are available, where only one technology is available. So most of our Asian and European countries, if you try to see, they have only NB-IoT rather than the other areas where they have both the technologies and both the options for them. So to summarize what we have done up till now, LTE-M and NB-IoT are both used for IoT designs, and mobility, if you want, LTE-M is better choice for moving devices, and coverage, it is, we have to check the map where it is predominant and we have to go along with it. And local GSM operators will tell what are the good deployment options available to us, because already the GSM stations have been laid down. The infrastructure is there. So you can contact the local operators and see what is their 2G layout, and other operators what is their 2G layouts and all. And you can see whether the air corridors are covered by that or not, and then use that technology. Power consumption, if you try to see, LTE-M and NB both are low power only. So both will give you a better lifespan up to 10 years and so on. And both have the wide area network concepts, and power consumption depends on the application and condition. This is prime important. The applications, if you try to see, they are, we can categorize into three types, right? So one is, see, when you are driving a car, the engine temperature has to be constantly monitored. It is not that I'll monitor now and after half an hour or after 1 hour and so on, right? So there are some applications where you need continuous monitoring of system or continuous data exchange, we call it as. The second type of application is periodic. For example, I am monitoring the temperature of the day. I need not have to do it at 10, 10.05, 10.06, 10.07, 10.08, and so on up to end. If I measure at 10, 10:15 I can note it down, 10:30 I can note it down, 10:45 I can note it down, because the variance is very small, right? So we call it as periodic monitoring. One is continuous monitoring, the second one is periodic monitoring. And the third one is event-driven monitoring. Like, for example, I kept a camera in the corridor, right? I need not have to wake up in the night at 10 o'clock, 10:15, 10:30. Periodically, I need not have to wake up and see. I call it as event-driven monitoring. When there is some mobility, it gets up and tries to monitor things. What we call it as event-driven monitoring. So these applications, three applications, what we have, continuous, periodic, and event-driven monitoring, will tell the way the battery is consumed by the device, right? So in IoT also, when we can separate the applications, like for monitoring the various blocks in the IoT might be continuous in nature, right? They have to continuously see all the fans are running at the same speed or not. And the angle at which it is rotating, we have to find it out. So there are some part of the application which have to be continuously monitored, some has to be periodically monitored, some has to be event-driven monitored, right? For example, I am driving a drone and I have to take a picture of the, let us assume that there is a small forest in which a tiger is moving. I have to take a picture of the tiger. So I'll be monitoring. I'll not put the camera on completely from this end to that end. I want to see wherever there is some type of mobility or movement of some leaves or something, I can take a picture of that and see whether the line is there. That way I can consume a lot of energy on my device rather than continuously putting it on. So the application will tell again the life of the device, right? So that is more crucial over here, and that tells directly the power consumed on the device. So depending on the requirement, we try to categorize the requirements and then use specifically for the job only. We will not put it always on, okay? The transmission rate is again an important thing. We have to send the data to the base station and take the comments and all. So LTEM is much better choice in case you have a larger data. And if it is small, then you can think about NB-IoT. Okay. So use cases, if you try to see, there are a lot of use cases available. Smart meter, NB-IoT, because the data are very small. And smart city application like air quality monitoring and all, still NB-IoT is sufficient for data of these air qualities and all. GPS takes a longer data and all, you need LTM. Mobile point of service terminals and all, LTM. So I think we have just summarized the two technologies, which is good and which is bad. And if you have an infrastructure layout of the 2G base stations from your local operators, you can still design your own air corridors for that application. So now come to the MIOT. There is one more, is the unlicensed. We are entering into unlicensed band. And this is the paper from where it has been taken. So you can see that we have three options over here, MIOT, LoRa, and Sigfox. And we'll start with MIOT. We then compare the other two also. So MIOT is a low power wide area LP WAN, we call it as low power wide area network protocol. And it is used for massive IoT connectivities. It is not that you can connect only one or two or thousands of devices can be connected together, right? And you can, the message is divided into sub packets and transmitted in time and frequency also. I think sir will be explaining you on time, frequency, space, multiplexing and all. And you can see reduced on-air time when you combine with pseudo-random sequences and all. The channel coding is also superior, and it is such a way that it is being protected from the interference also. Interference will not come in. So if you try to see, there are two terminologies which are popularly heard by even Professor Kamesh and the other professor also, Vanka also, that they have commonly used two terminologies called interference and noise. And basically, if you try to see, I'll just give an example of what is noise and what is interference. So let us take a class and some boy is eating the table. This is not interference, this is noise, right? So when I am speaking, again, if two more students are talking loudly, that is what we call it as interference, right? So the voice frequency, for example, I am using at 3.4 kilohertz and the same voice frequency 3.4 is there. So they both will try to mix up. If we observe the signal on a CRO scope, we will see the signals getting added up or subtracted because of the same frequency. But when we try to look into a different frequency, it is not interference. That can be easily separated because the talk space is a separate frequency band. Okay, so please remember that the noise, it can be self-made noise or man-made or environment condition, they are different. Like for example, device, they generate noise because the flow of electrons and all will create noise. And there is the external noise is like when you are trying to talk, there is a train in which you are sitting and talking, the train is a noise. It is not interference, it is a noise, right? So the interference we try to speak when we have two people using the same frequency. So we have co-channel interference and adjacent channel interference. If we can separate them out in space, then the interference goes to zero. Suppose I send these two boys outside to talk, then interference is reduced. right? So we have to see that whenever we have two frequencies coming together or adjacent frequencies coming together, you separate them spatially so that the signal dies out over here, right? Because they slowly dies out with the D. So you move it as far as possible so that the signal will not affect the noise. So if there are other ways of removing it also, but basically you should know that noise and interference are two separate quantities. They have to be dealt in two different ways. It is not the same way. So, and MIOT has a coverage radius of 15 kilometers, very competitive with the NB-IoT and the GSM, EGSM, and the LTEM also. Okay, the coverage is almost equal to them, but the only thing is you have to remember that the messages are sent in a different format. If you try to look from the number of base stations required for the complete coverage depends on the extent what the city is going on. For example, most of the towns and cities have a circumference of 15 to 20 kilometers. They don't go beyond it. And that is for a large city. If it is small town and all, they only go to 5 to 10 kilometers circle only, right? So if you look like that, the number of base stations required for covering it is very small, right? 1 or 2 base stations are sufficient to cover all the complete city and town, right? Or 4 places might cover the complete region also. Okay, with few base stations, the required coverage is done. But when we are trying to look for a larger distance from 100 kilometers and 200 kilometers, the number of stations are not small. You have to use the multiplying factor for that, right? So the another advantage with this MIOT is it can go to the places where the cellular technology cannot reach. For example, if you try to go into a cellar, you might not be able to get a mobile call and all. But with the help of MIOT, you can see that you can reach to a place where you have blind spots or places where the signal cannot travel also you can have. And that is possible to have if you have a flexible base station. What is flexible base station? Like bending the base station? No. It is flexible means nowadays we are getting programmable interfaces also, interfering surfaces also, integrated services, okay, intelligent surfaces also, where you can program the surface such that the signal goes into your cell, right? We call it as repeaters and some people call it as relays and all these things, right? You can extend the Wi-Fi to some more distance. You call it as extend. So if you have some surfaces like that, you can reach to blind spots also, right? Okay, so this is another important feature. The battery life can be extended. That's what we have told, 10 years of coverage also you can go up to. And it can withstand the co-channel interference. This is another important thing because you are using some pseudo-random codes for generating that. You can have some orthogonality built into it so that the interference can be reduced. Most of the cases, the orthogonal codes will help you in reducing interference, right? If you give different codes for different frequencies, at the other side you can remove it also. Okay. So this is again the same thing. Blind spots are indoor penetrations and secured home environment. This is one important thing which you have to keep. And the another important feature which is very much suitable is the speeds of 120 kilometer per hour. Okay, you can still get connectivity if your device is traveling at 120 kilometer per hour. And this is almost like a normal speed of a drone, right? If you try to see a drone, drones fly at 100, 120, 140, this range only. It cannot go beyond that. Okay, we don't have high-speed drones to carry these deliveries and all these things. And coming to the next LoRaWAN, this is again a ultra. You want something on the previous slide? No. This is again a low power, ultra low power, where the lifespan can go up to 10 years. This is another important feature. You can see it's a single coin type of cell. You can go up to 10 years. That is the beauty of this one. And the distance is 10 kilometers. and up to 3 kilometers if it is a very dense urban areas. Dense means long buildings are there, which where the signals get multiple reflections and go. You can see that in that cases it can be up to 3 kilometers. But if it is a spread out city or a urban or a, you can call it a satellite towns and all, it can go up to 10 kilometers, right? And this also have a deep indoor penetration, and multi-floor connectivity also is possible. And this is a license-free spectrum. We are only dealing with unlicensed spectrums. And you can see that the device locations can be easily found out. Okay, this is added advantage because when we are trying to use for drone, we need to know where exactly the drone is, right? So it helps us in finding out even without GPS also. This is one advantage what people are trying to look at. Without the help of GPS, you can easily, using triangulation, you can find where the drone is at that given instant of time. And if you know the velocity, you can predict the next point, right? So this is something like a point process only. With a known distance and known velocity, you can easily interpret the next time it can be at this point, and next time it can be at this point, and so on, right? So this is one advantage is what you get out of LoRaWAN. And it's not only that, the other thing is, for example, there is a street lamp which has been kept and somebody has picked it up and moving, we know where it is, like dustbin, smart dustbins. Somebody is picking up and going, we know exactly where it is, right? So there is an added advantage with that. And mostly we don't use for street lamps and all, we use for vehicles collecting the dust. We can know where exactly the vehicle is, and we can send a note to the next lane saying that the vehicle might come to your place by 5 minutes, right? The garbage collecting van, if it is moving, we can track it and say that, okay, after 5 minutes it come to your house. We can send a SMS to the customer saying that within 5 minutes the vehicle might come. Our water delivery, we can say 5 minutes the water delivery will be done, right? So these are some of the add-ons what you can do along with the technology what you have. Okay, so this is another important thing where people are trying to look. And for us, it is very useful to predict the drone passage also. And if we know that, we can see that the other drones are not coming in the way, right? For the drone communication, location is the prime important thing where the technology like LoRa and all will help us in finding the location and predicting the path and intersection, avoid the accidents, avoid collisions, everything can be done, right? And it has a high capacity also, like lot of messages can be exchanged. The bandwidth is high, you can send a longer messages and so on. Okay, so this is one important thing what we have to understand is there is a public-private deployment. And this is helping us in realizing a lot of application in smart cities, smart transport, smart health and everything, right? And we are only trying to wait and see how the drone technologies will get advantage out of this, right? Because with this private and public deployment, the people who are coming forward to invest money, they can deploy a base station and collect the revenue out of it, right? So this is, we call it as PPP arrangement where public participation and the private participation takes place, like the toll plazas and all on the road, right? There is government and private parties will participate and they'll give like lease, 10 years, you collect the money and go. After that, it belongs to God, right? So such type of things can be done easily, and software and all are available right now. People are trying to use it, and it is almost ready for deployment also. All the technologies are available, and we are also having some hardware of LoRa where we are trying to connect and establish connectivity and all. Security is also very high. It is 128 AES algorithms are used. This is advanced encryption standard, we call it as AES, and that is being used. And the another advantage with LoRa is like Windows, whenever there is a new security, automatically it gets updated. So whenever there is a new development, you can directly upgrade all the LoRa boards directly. You need not have to bring it, upgrade it, and take it and all. There is a auto upgradation mode where automatically set of devices can be upgraded with new securities or new firmware or new software. Automatically you can do it. You need not have to bring all the drones together. Okay, with one stroke of the key, all the drones will get updated. So there is a roaming facility. There is handovers are done directly, and we can use this for your communication purpose. But only thing is, it is a unlicensed band. No, this comes under the licensed band only. This is unlicensed moiety, and this is LoRa. This is unlicensed band, so we have to be very careful while using it for commercial purpose. Right? Drones, when it comes for commercial purpose, it has to be carefully dealt with. It has to depend on the local government for the rules and regulations. Right? So this is something like a open source software, so open source hardware, everything is open. We can use it and we can go along with it. But only thing is the local government policies and all will affect the performance of the network, right? And there is a consideration in the defense, like they want to make the 848 or 78 frequency free for this communication in the defense. Right now, I think it is not there. Only 488 is there, but now they are planning for a second band to be released for the communication purpose. The next one is Sigfox. This is also a very reliable solution and a low power solution, and there also a lot of devices can be connected, but this only exists in USA, not in other parts of the country as a continent. So please see that these are in Europe, they use uplink and downlink, and these are the down channel frequencies, 100 by 100 in EU and USA 600 Hertz they try to use, and in uplink they are using these transfer rates. Okay, data, this is channel bandwidths, and this is the up and down data rates. Okay. So Sigfox is not that popular in India. We don't have the Sigfox technology devices or the technology available for us, whereas the otherwise it is popular in US. And the another important thing, as sir was saying, is Doppler sensitivity. It is unconstrained, so they can easily use this for their technologies, and they are using it also, right? Because the Doppler sensitivity is unconstrained, so it doesn't have any effect on it. It can be usually used for the high-speed mobilities and all these purposes. Right? So now this is a comparison of these licensed and unlicensed band, which tells us something more on how to go along with the technology. And this is also neatly written by Okali and Kabaso. So if you try to see from these two are licensed one and these two are unlicensed one. And if you try to compare the frequencies, you have unlicensed and the licensed one. Oh, sorry, these two are unlicensed and these are licensed. So the bandwidth, if you try to see, the unlicensed is very small compared to licensed one, right? If you compare the licensed one, you have a higher bandwidth than the unlicensed one. And in if you take LoRa and NB-IoT, they are almost identical. Yeah. Yeah. Doppler sensitivity. If I am standing here, if there is something moving, coming towards or going away, that will not affect it. It is not the mobility of the transmitter and receiver. They say the Doppler sensitivity is unconstrained, but they are not trying to compare with respect to a network. They are only trying to talk about the transmitter and receiver, right? So when we are trying to look from the parameters what we are trying to display, since Sigfox is not available for us, we are just trying to put the mobility as 0 because the speeds at which it is traveling is very low. And they are not tried, they are still experimenting with the drones and all, but what they are trying to do is with these smart city applications, mostly water flows, they have tried it. They want to monitor the water consumption at each and every place and all, where they are only using it for flow control. They put a flow meter and try to control over there. It is not strictly the device mobility, it is the water flow mobility they are trying to speak. So now if you try to see the mobility also, if you try to see, even when we say LTE and NB-IoT, we have said that mobility is not good in one case. What is it? See, we have shown that one slide saying that mobility is better in case of LTE-M rather than NB-IoT, right? It doesn't mean that NB-IoT is 0. It only doesn't provide handover. Handover means within the cell they can move, right? It cannot go out of stop. That's what I'm saying, that Sigfox also. Within that reason it is good. We are not trying to look for running on the road and all. Right? So when we say mobility, please remember that it is not out of the cell range and all, within the cell range, and that also is small in case of Sigfox. Right? Even in the cell also, it is not trying to, only trying to see whether you are trying to get the data towards your center or going away from it. So this is localization. All the things are helping you in localization of the device. And link budget, if you see, all of them are almost similar. And the payload, this is more in licensed band than unlicensed band, right? Yeah. Okay, the data rates are high in case of licensed band than unlicensed band. And the coverage, if you try to see, the unlicensed LoRa and Sigfox gives a better coverages than the licensed band, because the most of the cases, if you try to see, the operators like Jio and Airtel and all, they want high revenue out of the users. So they go to the place where user density is more, right? And like for example, you will not find a Airtel or Jio network in North Kashmir or Northeast regions and all. There the BSNL only works, right? So we have a very good concept in India, like we go for auctioning of spectrum. I think you might have heard. There is a small band which will be auctioned and people have to participate. And BSNL also has to participate. It is not that they are government so they get free. So when a spectrum is given, for example, for Telangana, they are trying to sell a spectrum. So all the bidders will try to put a bid in the procedure, and whoever bids high will get it, right? So the BSNL will not have so much money to put it over there. So they will not be good competitors for these areas like Telangana or Chennai or for Bangalore and all. But if you try to see the bid patterns in the Northeast region or in the Kashmir or some places and all, these people will not put heavy amount because the user density is very less. The revenue what they get from the investment what they are doing is very less, right? So their BSNL will get the bids. And if we try to look from that point of view, you can see the coverages. When there is a heavy dense urban areas, the maximum distance go to 2 or 3 kilometers or less than that. If you want good coverage, it will be only 1 kilometer and so on. So in that case, if you try to see the LoRa and all, they get better coverages. And why they get it is, there is a technology which they can be used to boost the signal up to that. right? And here these people have a restriction of that because the spectrum is given only for a small area. They have to use within that radius only. And another important thing is, I have this much capacity of users to use in a cell. So if I reduce the cell use size, I can use the same quantity again in the next set, right? If I reduce the cell sizes, I can repeat that in a spatial division multiplexing, right? So I can increase the user density. In a small area, I can put more number of users, right? But the same if you try to take in LoRa and Sigfox, the user density will not be that much. So they can spread out the signal to a larger extent. That is one reason, again, you can think of urban 1 kilometer and urban 10 and 5, because this is defined by the user density, not by the signal strength. So if there is more and more users in the area, you have to put more and more base stations, right? So that limits the distances. If you take one base station, it can go only up to 1 kilometer in urban, dense urban areas. Whereas here, there might not be so many users in that, so they can expand the area. Okay. In case of rural also, it is same. So they can go up to 20, 50, and so on, because the number of users are not there. They can increase the cell sizes and okay. So these are some of the important parameters which we have to keep. A battery life is almost same for any technology, because all are equally competing with each other. So they are identical. Right. So this is one slide which tells us the way we have to look at different technologies, whether it is a licensed or unlicensed, and it is very good written by this paper. So now coming back, we have covered these two, and this is left with us, right? So if you try to look from the cellular point of view, we are looking into this. We have going from 1G to 2G, 3G, 4G, 5G, and 6G. This is the source of this print, the picture. So we have started with analog communication in 1981, and we have moved to 2G in 1991. So we have digitized the signal, analog signal, and we are using GSM. And in India, we have not seen 1G, we have directly gone to 2G, right? So from, you can see a decade-long journey. 81 to 91 is one decade, 91 to 2001 is one decade, and 2001 in 10 is one decade, and 2010 to 19 is another decade, and 19 to 29 is another decade. But we will see that by 26 it is there, right? So it is not that overnight we are trying to get into a technology and we are getting it. We are spending sufficient long time for going from one decade to one technology to other technology. But please remember that in India, we have not seen 1G, we have not seen 3G completely. From 2G, we have jumped to 4G, and 4G to now we are going into 5G. It is almost very late in going into 5G, and almost by the time we came up, it is 6G, right? So this is again a good picture by Tanveer. He has given all the existing technologies available, what are the different communication modes, what are the technologies available, everything is given over here. You can see there is a satellite link, and coming down here you can see there are internet things talking to each other. Trees are talking to mobile, trees are talking to trees, and there is a hospital, van, drone, everything are talking to each other. And you can see that there is a infrastructure to support this type of communication, and there is a vehicles which can be communicated and so on. And you have GNB nodes, which is a 5G nodes, you can call it as, which is there. And there are, you can use a lower orbit satellites for emergency communication and monitoring the drones, and aeronautics broadband for communicating with aeroplanes through satellites. And you can have a GNB with beamforming, connecting each beam to each person, right? And you can see that there is intelligent transport, mobile broadband, SANE base, and C communication, and edge computing, cloud, computation, everything is available. So I like this slide from these people, and I just kept it so that all our whatever we talk in different fonts, everything is existing over here, which is the physical realization of the today's network, right? And you can get it from this paper. There is nothing secret about it. And the same people has compared the 4G, 5G, and 6G to give an vision what is next to present thing what we are trying to look at. So the years is decade long, but this is almost like a decade only you can keep it. But if you want to see the full-fledged things running, 28 might be the dead year to get it, right? So core architecture is all internet-based. What does it mean? Internet-based means packetization only. Everything is packet-oriented networks only, packet networks only. There is no circuit networks or there is no hybrid networks and all. Everything boils down to a packet exchange only. Okay, and you can see that it is the core network. TCP/IP will still run. All the IP packets will move around. And the multiplexing technologies, if you try to see in 4G, we have used OFDMA, single carrier FDMA. We have used, and that is BDMA and BFMC. What are these one? FBMC. You can check it up on your mobile. FBMC and OMA and NOMA. These are the another technologies what we are trying to look at. And mostly, if you try to look at these architectures of OMA and NOMA, they are strictly power based, but still how to use that for a same plane users is still to be understood, right? If they are far away, we can use NOMAs and all, but if they are on the same plane, using the technology will be difficult. Filter bank, yeah, okay. I think these technologies are same thing only. So if you try to see that the bandwidth available for 4G is only 20 megahertz, 5G is 60 megahertz, and we are expecting that in 6G you get 3 terahertz bandwidth. It is not communication. So much bandwidth is available for giving to users. Okay, so we are expecting around the peak, if you see the peak data rates, 1 GB, 10 GB, 1 terabits per second speeds, you are about to get it. Okay. So the switching is packet switching only completely, and different types of coding can be used, turbo codes, LDPC codes only, and the latency is more important, end-to-end latency. It is not device to device, end-to-end, right? So that is dropping to 1 millisecond or less than 1 millisecond delays. We are about to get it, and this is primarily important for a robotic surgery. Suppose one robot has done a cutting, the other robot has to do something else, and third has to stitch or something. If the latencies are not that good, if it is more than 1 or 2 seconds, then after cutting here, the other robot will wait for a command, and by the time the blood might flow out, or something might happen. So the latencies have to be very carefully dropped to a microseconds or millisecond, less than millisecond, so that the operations like robotic operations and all will be successful in this case. The spatial efficiency, if you try to see, spectral efficiency, 15 Bpps per hertz, and that has been doubled and that has been tripled, right? Means the data rates have been increased drastically high. Mobility, 1000 km per hour, which means that even in a bullet train, you should be able to talk to your friend, right? And now this 5G only, there is a plan to provide users with mobile access also. In some of the aircraft, they are giving the facility like users can talk to their base stations or to your friends and so on. But in 6G, it is possible, like people can talk to on aeroplanes to each of the other plane if they are carrying, and there is a bullet train which is running at 600, 700 km per hour, they can still have the connectivity, right? Satellite integration, fully connected. There is no connection up till now, but in 6G you will have full connectivity. And AI support partially is there, but fully supported. Like yesterday I shown a slide that everything is machine learning connectivity. Right. Autonomous vehicle support, fully supported, right? XR supported, fully supported. Haptic communication, fully supported. Visible light communication, yes. Maximum frequency is 10 terahertz. Architectures is intelligent surface models, we are trying to use it. And if you see service levels, tactical, connectivity density 10 to the power of 7 devices per kilometer square. If you take 1 kilometer square, you can put so many devices can communicate to the network. And the air traffic capacity is 1 gigabit per second per meter square. And this helps us to realize the drone architecture aerial networks comfortably, right? And you can see network efficiency is too high and spectral efficiency is too high compared to 4G, and reliability is 100%, almost nearing 100%. It is not 100%, nearing to 100%. So this is what expected with the 6G. And we have right now 5G with us, right? So now if you try to see the architecture of the 5G and the way we have to analyze it is, right now we have a connection density of 10 to the power of 6 per every kilometer square. And that will be improved to 10 to the power of 7. It is one more zero will be added for that. And latency of 1 millisecond is what is expected, right? And this is advanced, which means that it is 5G plus, it is not 5G, right? The inner one is the 5G, and this is 5G plus what we call it as, okay? So the network can provide 3 types of services to the user in the 5G. One is enhanced mobile broadband for the users who want high data rates, and it provides massive mission type communication where the number of devices in the network will be 10 to the power of 6 devices per kilometer square, and there is a ultra reliable and low latency communication where it's for industrial IoT or robots and automation plants and all, right? Where you have mobility and latency at your end, you need something like high latency, and reliability is also more important because when the device or cars are running, you cannot remove a connection and put a connection, right? They should be always connected mode, and they have to be low latency between the communications. And this is energy efficiency because all the IoT devices are running on battery. We need some type of energy efficiency and connection density. These two are primarily important. Whereas in the case of enhanced mobility, area traffic capacity and peak data rates. So in a given mobile users, we have to give high data rates for them. This is what we got it from this 5G is happening now. This is a very old one. So you can see that the applications in the EMBB is 4K or 8K or ultra high definition TV services, video services, and then AR, VR, and then you can say cloud gaming, enhanced mobile media, broadband, home TV, and wireless broadband, in-car operations. Right? So this is one part of it. Coming to ultra reliable low latency communication, you can see industrial automation, remote surgeries, manufacturing, self-driving cars, ultra reliable application like drones and aerial communications and all. And massive mission times, smart homes, smart buildings, smart transport, smart agriculture, smart cities, everything comes under it. So the 5G network can cater to 3 different types of applications, and they you can see that we are only interested in this type of services where ultra reliable and ultra low latency communication can take place between and among the devices of aerial communication. And this is a very beautiful slide from Juniper, and this tells us how we are able to do in 5G and 4G and 6G and all. So if you try to take the earlier networks like the traditional networks, what we have, I think most of you might have seen that there is a base station and there is a small cabinet where they keep an AC and put all the equipment in it. The earlier stations, what you are trying to see, right? So there is a base station and there is a housing small cabinet type of thing where you keep an equipment and put AC and generator for it to continuously run and all, right? So now, what would the technology changes have done is all these base stations are connected to a packet switch network, a core network somewhere, right, by means of fiber or whatever. So now, as the technology is changing, what people are trying to do is they have separated these BBUs into two parts, right? They separated the BBUs into two parts, and they are trying to do some operation on top of it. Like we have two planes in a unit, right? One is called as data plane and one is called as control plane. The control plane will try to control how the data has to flow, how many users have to be given, and all these things. So in most of the cases, what we try to do is we try to push this one into a cloud and then connect to the control planes, right? So the control unit is something we are trying to keep it in common, and we only give data planes where we can program it for 10 users, so much band rate and all, right? And now in this virtual RANs, what we try to do is we kept these BBUs in a virtual cloud, not in the physical cloud, and we are trying to do this operation. And slowly you can see that this complete part is divided in two parts again, control unit and the data unit, and this data unit is connected to the base station, and this is only a radio heads. So nowadays we don't see that big cabins and the AC and everything at the base station. We only see a small unit at the antenna, and that antenna we call it as radio units, which tells how many radio channels have to be allocated to what, and it is software dependent. So for example, I have a campus like this, and the campus is closed by 5:30 and nobody is staying in this. I can shift these radio units to some other place and I can still use it, right? So that is what we call it a software defined radios, a network, where I can reconfigure my complete, because they are SDRs only. So I can program it and shift these radios to some other place, and you can utilize them in a proper way, right? So this is all we can do it in Open RANs. What we are trying to do, we have divided the unit into module, and we only kept the radio unit over there, and we are putting that unit in the cloud, and centralized we are trying to distribute the frequencies to different places and see that they are not interfered, and then try to communicate it. So now coming to non-terrestrial networks, if we want to integrate terrestrial and non-terrestrial network, we have different types of options. For example, we have connected and unconnected. Still there are a lot of areas which are not connected. If you try to take the agriculture field near the hill or near outside the city and all, you don't put an internet over there, right? So in such cases, in the 6G, we are trying to use some type of aerial connection. It can be drones, it can be HAPs, it can be balloons, whatever it is, or it can be LEO satellites. We try to monitor the complete field, and we know how much agriculture field is there in a city, or how much mining area is there in the city, or what is the waterfall in that place, we can see it, right? So I can say that this year the waterfall is this much, next year how much it is, I can predict it if I have historical data, right? And I can also see how much plastic is floating on the sea. Nobody put the internet on the sea, but now because of this option of aerial communication, we are trying to monitor a lot of things which we have not done earlier. So we can see that the environment control can be done. It's not only the pollution air, but even in the sea, what is polluted, we can find it out, right? And the water flows, we can monitor it and say that this year the water flow is less, next year it might improve or not. We can do some analysis on that. So you can also monitor the mining activities where there is no network somewhere in the out of the town and somewhere it is happening. You can completely monitor what is happening over there. Or you have a long pipelines flowing from somewhere, the water is coming in, or some gases are passing through, or some oil is flowing through. So you can monitor the complete line and see how they are flowing, what is somebody stealing it or not, or is there any break and it is leaking. Everything can be monitored. And it's not only that, even in the desert also you can be monitored, right? And you can see that these areas, it is not covered yet, but we are trying to bring it into the 6G coverage areas. In the sea, I want to monitor it. What is the fish population, I can monitor it. I can monitor what are the fleet which is flowing in the water, I can monitor. Or I can see what is the environment hazards, like oil spills or something is happening, I can easily monitor it and find out the location of it, right? And even on the mountain, how much snow has melted down, whether the snow level is up to there or not. Nowadays, we are seeing Atlantic, the snow is melting and there is no snow left and all. So I can know what is the rate at which it is melting, everything I can monitor, right? So these are some of the things which are not covered yet, but in the 6G, we are planning that all these things will be covered. And these are all will be covered by means of aerial networks only. It is not terrestrial networks which we are trying to use it. So you can see the application rates at which the use cases are being generated, and there is a high demand for aerial networks, and we have to look into aerial networks. Not today, tomorrow we have to look at it. Not tomorrow, day after tomorrow, we have to look at it. It is not that it is not our part. So this is another important example. In the forest, you want to know what is the destruction going on, fire is going on. Like you might have seen California, there is a lot of fire coming, even into the city it is coming in. The forest fire is coming into the cities also, right? Or if I want to know the water flow also, I can use it. Or I want to know what are the flora available in the forest, I can easily monitor it, right? I want to monitor the animals in the forest, I can do that, right? Or the birds in it, the flows, water flows, the caves can be monitored. So this is one specific use cases of the aerial networks, where the areas which are not covered or the areas people have not planned for it also are being brought into the umbrella of 6G. So now this is another scenario written by Hizolio, Shai and Chen and all, where in case if you have an aerial network, how to visualize the circles in a given circle, right? You have a larger area to cover. So with the help of these things, how I can cover the complete requirement, demand of it. So you can see with the non-terrestrial layers, there is extreme coverage, mobile bandwidth, broadband is available. So the broadband connection on the move can be had, wide range of IoT services, unconnected areas you can connect it, and you can also use for high precision positioning and navigation, and you can also use it as a observation protection purposes also, right? And now, why you need terahertz for that, terabits per second, why you need it for these applications, right? These are the applications which we are trying to look at. Why we need a terabit for that? So the applications, if you try to see, before that I'll just go into the 6G, what we are trying to get it. The latency should be less than 0.1 milliseconds. That is what, from 4G, 5G is here and 4G is here. From 5G we are reaching this point, and 6G we are going up to this point. Okay, reliability 9s, 99.99999 means, which is 100%. Then connection density, every square meter there should be 100 devices connected. Meter square means this is 1 meter square, there should be 100 devices connected in this area, right? And location precision to an extent of 1 centimeter they want. It is not that in 10 feet he might be there and all, exactly he is there, right? Or the device. Battery life, extend 20, 30, 40, 50. People want lifetime, but we are only obtaining up to 10 and 20, but people want still larger lifetimes. And energy efficiency should be 1,000 times small than what it is consuming now. So this is what the 6G ambitious plan is. And this is 5G where it is existing right now. We want to see how much this expands in all directions, right? So this slide we have seen it earlier. We are trying to put it back again because they are few critical things what we have to learn is the mobility is doubled, the speed is doubled. That is one important thing. The bandwidth availability is 100 times what we are having today. And you can see the reliability has increased drastically high. Packet errors have been brought down. And you can see the power consumption is ultra low, right? So this is one more important thing what you have to see, that the expectations are very high for the 6G, and we have to wait and see whether these things are being met with or not. So 2G and 3G is very small services, 4G is very small services, 5G has improved, 6G has a lot of expectation where you are completely digital world and you have a human world, you have physical world, all these things are combined into your 6G and you get a connected world together. Whatever you do, you know what you are doing it. Next time when you put a step, you know what you are doing it. If you are waiting for a car, the displays will be coming before you with all the parameters and all. Okay, so the speed, why you see a holographic telepresence demand. For example, this is 180 centimeters if you try to take. 180 centimeters is not too large, right? 6 feet. If I want a 6 feet human data, the data will be more than 1 terabit per second. And that is required for a doctor to know how the patient is there at the remote place. So don't say that 1 terabit is very high. It is very small in compared to the applications what we are trying to get it, right? If remotely a drone is taking a picture and sending it, that requires a bandwidth of 1 terabits to have a feel that he is looking and talking to a patient over there, right? It is not that after 1 hour you get the picture and then the patient will be waiting there for 1 hour and then the doctor talk to him, right? If he wants that doctor to interact, the patient is standing before him and talking to him. If he wants such type of scenario, he should have 1 terabit per second bandwidth so that the telepresence can be happening over there. Okay, so now look at the speeds. Okay, so if you are using the 5G network for that, it takes around 100 seconds to get that picture, right? 1 GB if you are trying to transmit it, you have to wait for 100. Size, the volume it is occupying, the block size of hologram is gigabits. If you want a color depth, 24 bit per color, and frames per second should be 60 frames per second for smooth operation. And if you use some reducing techniques and all, you can bring down 60 to 24, and then you see the data, what you are trying to transmit is a compressed data, it is not the original data, and that itself is taking around 1 terabits per second. This is only to tell you that the 6G expectations are not too high, but it is required for the next step of applications. Yeah, I stop over here. I give you a brief introduction about the various technologies used for the long range communication and how the cellular network will help us in communicating that. See, for example, if we take our mobile, we have options like for connecting to cellular, we have one network. For connecting to Wi-Fi, we have one network. Connecting to Bluetooth, we have one type of network. Connecting to my card, I have separate, right? What we are trying to, even laptop, if you try to take, it is having a Wi-Fi connectivity, it has a LAN connectivity, it has a Bluetooth connectivity. So now in Indian market, most of the drones have multiple technology. They are not having with a single technology. That is perfect. Coming to a long distance communication between the drones and all, They are still using most of the cases like 2.4 3-band, okay, means unlicensed band, okay. But they are trying to use Bluetooth and the Wi-Fi connectivity. Because most of the things are happening inside the locality, like inside the premises. So you have Wi-Fi inside the premises, so you are trying to use Wi-Fi for that. But you can also use LoRa's for that.
Suppose up to suppose I want to transfer data to 3 to 4 kilometers from I can say that from 4 meter to
3 kilometers you want to go.
then LoRa will be suitable.
But LoRa, most of cases LoRa, because we have the technology available in India, we can use that. Or in case if you are not having that, you can use eSIMs for that to connected cellular technology. eSIMs are there. eSIMs. So you can use that for connecting your drone and your device, and you can control using that.
We have option of LoRa and eSIMs.
LoRa is one. eSIM is connected to the cellular networks.
For data acquisition, I am asking.
Yeah, data acquisition mostly we are using LoRa. And mostly it is a closed environment. We are not going out of the campus and collecting. Because again, when you transfer for longer distance, the local government permissions are required. Right? If I fly a drone, next moment there will be a fleet of police coming and asking who is that drone and everything. So they are controlled by the local standards. We cannot use whenever we want. But for you, I think you have your own permissions. You can use it. But for local purposes, for drone deliveries and all, we are not licensed to move the drones in the air. Right? Even one experiment we are trying to do to monitor the traffic on the road. Right? And we want to know how many cars, how many vehicles are passing on the road to do some analysis. For that also we have to take local police permission. They have not given it because they say that there is a privacy act, you cannot monitor others' vehicle. Right? So I think you understood that.
Yes,
Privacy act, others can file a case that my vehicle has been tracked. And
It's suppose for air to ground we use LoRa. And you are talking about we can use hybrid also.
yeah, you can use multiple technologies.
So for drone to drone we
No, see. What I mean by local technologies, I can have a Bluetooth activated for my keyboard, for my headphone, for my mouse, and I can use Wi-Fi for connecting to it. That is what I mean to say multiple technologies. For monitoring the drone hardware itself, you can use some technology. And for communication purpose, you can use another technology.
then for if we go for the drone to drone then we can use for radio communication.
Yeah, for range communication. And inside the drone, you can use short range communication. That is one important thing. And especially if you want a good data rate and a longer coverage region, go for cellular. Because the LoRa base stations and all are not existing right now. You have to create your own transmitter and receiver. You have to put your own transmitter base station, and you can keep one receiver on the drone, and you can try to talk.
Using cellular, how encryption will be maintained?
Yeah,
If we talk about the respect of difference.
yeah. See, that's what I'm saying. If it is cellular, the call will be transferred automatically to other side. Right. So you have connectivity. You can get your call. Say, for example, you are here. Your friend is traveling by car. Still, you can have a connectivity with your friend.
Most of also like this.
No, that's okay.
Suppose
Suppose you call him using your mobile, you can still have connectivity.
in cellular maybe there are a lot of public also. So if they are intentionally want to interfere us, then they can interfere.
No, but that care has been taken by the cellular people. They will not give two adjacent frequencies for two. Right? So that interference part is taken care by the service providers. So you will not have interference.
So then how we distinguish both communication if same drone will communicate with you use the software for drone to drone, and same drone will communicate with the ground station for layer to layer.
It is not so easy, like, because when you establish a Bluetooth connectivity, you have an identification. Only the drones which have the password only can communicate, others will not able to. Even if I have a Bluetooth, I come here to it, I will not be able to communicate. For every connection, there is a code which will be given. For this Bluetooth, if the 7 devices are there, I have to give the code what it is given to the 7 so that they can only communicate. Code-based communication for security purpose, right?
So for 3 to 4 meter for suppose that we use complicate drone, that's maximum 3 to 4 meters.
Yeah.
Then which we can prefer more efficient.
No, if it is 3 to 4 meters, if you are trying to see, and nowadays we are trying to use device-to-device communication because the latency which it takes to ground station and come back is larger than what they try to come. So in that case, we activate the device-to-device communication. So for that purpose, there is a what we call it as handshake.
Yes, sir.
Okay, so two people will handshake only, they can talk. If they don't handshake, they cannot talk. So that procedure we try to see that interference is not.
So their Bluetooth Wi-Fi process can be.
Yeah, we can use any communication. There should be a handshake. If they say okay, transmitter receiver has accepted, they can exchange it.
So there will be different transmitter and receiver.
Yeah, different for the connection.
Load will be.
Yeah, that's okay. So any more questions? So we'll break out here. I think the tea has been we. We don't have a class after this.